Okay. Okay. Good morning to everybody. Welcome to the Multimessanger session. And we start with Professor Kentaro Komori, that is here, and you talk about the current status of the Seagull experiment. Okay, I will tell you.
Thank you for introducing me. Good morning, everyone. Today, I'd like to talk about current status of the SIGO and BD-SIGO on behalf of the SIGO collaboration. This one. These are contents. First, I would like to talk about the background of our collaboration, and I would like to explain about what is the SIGO and what is BD-SIGO. Then I will introduce the scientific targets of the SIGO and BD-SIGO. After that, detector configuration and the sensitivity. And finally, I will explain about the current experimental demonstration or simulation towards the SIGO project. But let's start from the background. So now the number of gravitational wave detections is drastically increasing even over 200. So this number is including the preliminary one in 04. So until 03, there are fixed detection number is 90, around 90. And after that in 04 until now, the event is increasing up to 200 in total. Then we know the population of binary black holes in the universe, and we detected binary neutron star. So multi-messenger astronomy began. Also, we can now test the general relativity with unprecedented sensitivity. And also we have additional method to measure the Hubble constant. And now it is on the multi-wavelength gravitational wave errors. So this video shows the various gravitational wave sources and frequency, including each corresponding the detectors. For example, at the very low frequency, around 10 to minus 16 hertz, there is a primordial gravitational wave measured by the CMB mode. Also, recently, pulsar timing array group reported the detection of stochastic gravitational wave background from supermassive black hole. And also, LISA in space-based detector will target at massive binary black hole merger around millihertz. In my talk, I'd like to focus on the space-based gravitational wave detectors. So this figure shows the various detectors planned in space. The vertical axis shows the sensitivity, strain sensitivity, and horizontal axis means the frequency. So the ground-based detector has lower sensitivities at frequencies lower than the mechanical resonance of the test mass, which is typically around 1 hertz. Actually, the displacement between the mirrors, for example, in the ground-based detectors, is proportional to this factor. So the delta L is displacement, and H is strain of the gravitational wave, and L is arm length, and this additional factor, omega square factor. So in the case of high frequency, much higher than the mechanical resonance, the displacement is this factor, so minus HL. This is typical, well, how can I say, typical expression of the displacement. But low frequency, it is proportional to omega square. So the sensitivity to the gravitational wave is drastically decreasing. So in order to detect the low frequency gravitational waves, we should reduce this on omega m mechanical resonance. In that sense, we should go to the space. A test mass floating in the space is almost absolute free mass. And it is enabling the detection of very low frequency gravitational waves. So there are various space-based detectors proposed. For example, around microhertz region, there's a LISA max, Astro DGW or something like that. And around millihertz, as you know very well, LISA or TaiZi Tianqin project. And also 0.1 hertz. In this meeting, we call this frequency as mid frequency. The detector is, for example, decihertz observatory, which is upgraded version, one of the upgraded version of LISA or Big Bang observatory, and DeCIGO. Okay, then what is DeCIGO and BDCIGO? It stands for decihertz gravitational wave observatory. The first concept is proposed in 2001. We can neglect the gravitational wave foreground from white dwarf binaries above, in particular above 0.1 hertz. So we don't have to subtract, use the technique of the subtraction. So this frequency region is potentially an optimal window of observing primordial gravitational waves from the inflation. So what is the originality of DeCIGO and BDCIGO? The originality is formation flying of 3 spacecrafts. So we will construct a Fabry-Perot cavities between the test masses in the spacecrafts, and which enable the unprecedented sensitivity. It requires sub-nanometer control between the test masses in the different spacecrafts. So actually, it is very challenging, but we would like to realize this technique. So we have 2 steps of DeCIGO and BDCIGO. So you can determine the meaning of B. We don't have the specific meaning actually. So for example, black hole or binary or the second alphabet. Anyway, we will do the 2 missions. The first one is BDCIGO. It is precursor mission for DeCIGO with a moderate sensitivity. And DeCIGO is, after that, mainly targeting at primordial gravitational waves from the inflation. This list shows, the comparison between DeCIGO and LISA. So the launch timing will be on 2030s in BDCIGO and still TBD in DeCIGO. So LISA will be launched in 2034. And the baseline is very different. So the LISA's arm length is 2.5 gigameter. On the other hand, DeCIGO arm is much smaller. So in BDCIGO, it is 100 kilometer. The DeCIGO has 1,000 kilometer arm. The flying scheme is also different. The LISA is constellation flying, but DeCIGO adapts the formation flying with more accurate, well, control. The orbit is basically heliocentric in DeCIGO and LISA, but BDCIGO is probably geocentric, but not determined yet. The interferometer is, in LISA, adapts the Michelson interferometer with transponder technique. On the other hand, DeCIGO uses the Fabry-Perot cavities. The displacement noise is also very different. The LISA, the displacement noise will be 10 to minus 11 meter per square hertz, but the DeCIGO and BDCIGO will see the 10 to minus 18 meter per square hertz. This difference is very huge, but not very huge than expected. I mean, so this displacement noise, so the 10 to minus 11 meter per square root hertz in LISA. This displacement noise is due to very small amount of light delivered from other spacecrafts. So the quantum shot noise of LISA is not so good. On the other hand, DCIGO and BDCIGO will use the cavity and receive the all of laser light from other spacecrafts. And actually, for example, in LIGO, they achieve already 10 to minus 20 meter per square hertz. So this 10 to minus 18 meter per square hertz is not so difficult. And the force noise is different. The requirement is in this 10 to minus 14 Newton per square hertz, but in this cycle 10 to minus 16 Newton per square hertz. This force noise is actually very challenging, so we should consider various force noise sources and address the issues. Okay, so what is the scientific target? At first, scientific target of BT cycle. So mainly the target of BT cycle is intermediate mass black holes. So this figure shows the luminosity distance versus the binary mass. The blue line shows the ET, red line means the BT cycle, and green line represents the LISA's one. So in BT cycle, so red curve, the binary range from 100 solar mass to 10 to 4 solar mass reaches the first error above the redshift of 20. This BT cycle bridges the gap between LISA and third generation ground-based detectors. And as you can see, if we combine these three detectors, BT cycle, LISA, and third generation detector like ET or CE, then we can realize searching for binary black hole merger detection from 10 solar mass to 10 to 7 solar mass beyond the redshift of 10. This means if we combine these detectors, we can observe almost all of binary black holes in the whole universe. Okay, what is the next scientific target? So there, another one is the early warning of binary neutron star merger. So in the right figure, we assume the binary neutron star merger localization, assuming the 1.4 solar mass at the redshift of 0.1. The source localization will reach the 10 to minus 3 degrees square at 1 month before merger. Also, the localization of binary black hole is very good. If the binary black hole of 30 solar mass at the redshift of 0.1, then the source localization will be 0.1 degrees square. And next, what is the scientific target of this cycle? As I explained already, the detection of the primordial gravitational waves from the inflation is a kind of final goal of this mission. If we if we can observe the primordial gravitational wave spectrum, then we can determine two parameters. So this figure shows the omega GW versus the frequency with the different tensor to scale ratio and reheating temperature. And BT cycle is shown as purple dotted line in the correlation measurement. So the first parameter is the tensor to scale ratio R, which is determined by the overall factor of the spectrum. And then if we are a kind of lucky, the decihertz will be the cutoff frequency of this spectrum. So if we can observe the knee in the spectrum, then we can determine the cutoff frequency of the primordial gravitational waves and then determine the reheating temperature. So DeCycle has a potential to test both of them simultaneously. And of course, there are other exotic sources expected from the other universe, like generation of primordial black holes or cosmic string. So this figure shows the detector sensitivities of B DeCycle and DeCycle. So the B DeCycle sensitivity is shown by the cyan line, solid line. At 1 Hertz, the strain sensitivity is 5 times 10 to minus 23 per squared Hertz. At 0.1 Hertz, 10 to minus 22 per squared Hertz. And mainly, these strain sensitivity are dominated by the quantum noise. In the case of DeCycle, at various frequencies, the sensitivity will be 10 times 1 order of magnitude more sensitive than the B DeCycle. And if we achieve the DeCycle sensitivity, and if we can take the correlation measurement with that sensitivity for 3 years, then we can achieve this black dotted line labeled as a DeCycle 3-year correlation. Then we can reach the inflation gravitational waves with this sensitivity at the star's position. This frequency is 0.1 Hertz to 0.2 Hertz. Okay, so we are researching the noise budget. So there are so many noise sources. At first, the sensing noise is mainly shot noise, and laser frequency and intercity noise are also a problem. And there are many false noises at low frequencies, as shown by dotted line as a wall below the 0.1 Hertz. So this figure shows the noise budget curve, so the strain sensitivity versus the frequency. The laser quantum radiation pressure noise is one of the dominating source. And also the residual gas noise in the spacecraft will be also a problem. And thruster attached to the spacecraft will be noisy. Yeah, actuator noise, magnetic noise, thermal radiation noise, something like that. So we should optimize the detector control parameters to reduce all of the noises well below the requirement. It is also a challenging technique. So how we can sense and control the length of the arm in B DeCycle and DeCycle. So there are 2 proposed interferometer configurations. The first one is a kind of traditional configuration, the differential Fabry-Pellin interferometer. In this configuration, the laser source is 1 in each spacecraft, and then injecting the laser to 2 cavities and subtract the 2 signals from these 2 cavities. Then we will detect the gravitational waves. The advantage of this technique configuration is it is a mature technique, but the disadvantage is this method requires the sub-nanometer displacement control. On the other hand, the second one is called backlinked Fabry-Pellin interferometer. This configuration, so there are 2 laser sources in one spacecraft, and we will take the bit node of them behind the laser light source. The advantage is we don't have to do the sub-nanometer level control because we can use the laser frequency control. And the disadvantage is it requires very good phase meter, better phase meter than LISA's one. Okay, so finally, I will talk about the experimental demonstration. So the first one is the demonstration of backlinked interferometer. So we demonstrated that technique at the tabletop scale in lab using a spacer including 2 cavities, which is shown as the left bottom schematic picture. And then we succeeded in this technique by reducing the frequency noise and discussing the limit of this subtraction factor of the frequency noise. And we need the pre-stabilized laser, so we are developing that. So the requirement of the laser frequency noise of the laser source is 1 Hertz per square root Hertz, around 1 Hertz. And we succeeded in satisfying this requirement using iodine stabilized laser. So you can see the green flash in the right up picture. So typically in gravitational wave detectors, we use the light whose wavelength is near IR 1064 or 1550, 2 micron on the 1 micron level. But in order to avoid the diffraction of laser light through the cavity in the space, we should use the wavelengths as short as possible. So we will use a 532 or 515, so the green laser, by generating the second harmonic of the laser source. And also, we will try to further stabilize the intensity noise at the specific frequencies. So the right bottom figure shows the result of the frequency noise spectrum. The green dotted level is 1 Hertz per square root Hertz, which is a requirement of this cycle. And the red curve is stabilized frequency noise. There is another simulation work. So we are optimizing the BD cycle attitude. So analytical calculation of relative acceleration, considering J2, lunisolar, gravity, atmospheric drag, and solar radiation pressure. Then we found the attitude with the smallest acceleration added to the spacecraft. So we want to suppress the added acceleration added to the spacecraft as much as possible. And actually, we found a good position at 80,000 kilometers from the space. Another experimental demonstration is the bidirectional favorable cavity. So we will construct cavity between different spacecrafts. And so we have 3 pairs of the interferometer. So in total, the cavity is the 6, and 2 cavity, well, 2 cavities are common. So it is the bidirectional fabrical cavity. So we demonstrated this technique with the injection of the differentials. And we combined angular controls of the test mass and beam pointing controls. Also, we will do the quantum locking technique to reduce the quantum noise further. It is a demonstration for this cycle. So to maximize signal to noise ratio of primordial gravitational waves, quantum radiation pressure noise of the laser light should be reduced further. So we will make additional cavities inside each spacecraft at the back, as shown by the left figure, schematic figure, and measure and reduce the radiation pressure noise by optimal feedback. And we also did the demonstration of that, and it's good result. And yeah, finally, I would like to introduce this demonstration. So measurement of relative velocity at link acquisition stage. So before locking cavity, the relative velocity between spacecrafts should be low enough, should be reduced from the 1 centimeter per sec. It is a conservative GPS level to 1 micrometer per sec. And we will use the Cerodyne modulation to laser frequency. It will give the effective offset to the velocity and enable the measurement, including the sign. So if we use the asymmetric Michelson interferometer, we can count the fringe of the Michelson output, and we can know the frequency. But only with this technique, we can know the absolute value of the velocity. We don't know the spacecraft is going away or coming to our side. But if we add offset, we can measure the velocity, including the sign. This demonstration is ongoing. Okay, let's summarize my talk. So mid-frequency, in particular, 0.1 Hertz, gravitational wave observation will bridge the gap between third generation detector and LISA. This frequency is a potential window to directly observe primordial gravitational waves. And our approach is BD-SIGO and D-SIGO, measuring not only primordial gravitational waves, but also intermediate mass black holes up to the first star era, and contribute to the great localization of the mergers, binary mergers, and the simulation and experimentation, demonstration and going. Okay, that's it. Thank you for your attention.
Right. Thank you, Dr. Komori, for your presentation. Do you have any question from the audience? Yes.
So thank you very much for your presentation. Can you remind us how long will a binary neutron star remain in the band of the detector?
Yes, so could you go to page page 7? I forgot the number. So around 0.1 Hertz, it is 1 month or several months before merger. So we, yeah, I guess so. Oh,
7.
Thank you. Sorry. I will do that. No. This one. So,
This is for a neutron star.
yes, yes. So 0.52 Hertz is 1 month before merger.
How long will you be observing? 1 month, 1 year?
Yeah, so yeah, several months. Yeah. Yep. Yep. Well, at this moment,
Distance.
mhm.
No, siamo,
Yes, yes,
siamo giusti.
yes, right. So at this timing, the signal to noise ratio, so I forgot the specific number, but not very large, but on the cycle number observed is large. And also we can measure it with the orbiting on the spacecraft. So the localization will be very good.
Okay. Technical question. Can you go back to slide number 6? Okay, I have the impression that the requirement for the displacement noise compared with that of LISA is much more stringent, even if you take into the account the length of the arms and the finesse. Why
So
you are
actually,
so
right. So it is a good question. So the displacement noise of LISA, this number is due to the bad shot noise. So LISA can receive only 100 picowatt from the other spacecraft. So the sensing noise on the laser quantum shot noise is not good. On the other hand, in the DeSigo case, okay, in the case of DeSigo, we can receive all amounts of laser power, so the shot noise is good.
So there is a contribution even.
Yes.
Okay, I have 2 more questions. No, first there is the lady and then here.
Thank you. My question is regarding the orbit for beta SIGO. So you said that there's acceleration dependent altitude, you need about 80,000 kilometers. So what kind of an orbit are you looking at this geocentric, right? It's
Yeah, it's geocentric. Yes.
So it's a circular orbit at 80,000 kilometers?
Yes, yes.
Okay, and second question is that do you have a constraint with respect to spatial displacement about a centimeter per second?
Mhm.
Do you have any restriction regarding angular separation, rotation?
Well, angular level is so that we can use the star tracker,
Okay,
and angular resolution will be the order of 10 microradian.
so that's not an issue.
Yeah,
The linear displacement is an issue.
yeah, yeah.
Right.
Yep.
Thank you.
Okay, the last question here.
Yeah, I was wondering, is there any plan to target for example, continuous gravitational wave from high spinning white dwarf or even magnetar, because spin seems to be in that range. Is there any plan?
Yes, yes. Actually, the additional source target is white dwarf binary merger or other white dwarf related one. But well, actually, it is just proposal, not very specific plan. But yes, there is.
Okay, thank you again, Dr. Komori.
Thank you so much.
And before moving to the next speaker, here's a video from Dr. Morosi introduced by Professor Ruffini.
Well, we had many moments very important in the meeting and still ongoing with this beautiful presentation. But what has made success of the meeting has been this gentleman who has participated and created in Pescara this technology of having the projection of the meeting so clear and really outstanding. It has been a contribution of Pescara, I would say not equally, but equally impressive. The use of Arum, the use of the campus of the university, but was made possible the vision and the transmission of these beautiful images has been this gentleman.
Thank you so much. I can see the video now. 1 minute. Okay. Thank you so much. Thank you so much. I need to translate Professor Ruffini because my English is not very well. And so On Display ha voluto sposare questo progetto perché crede fermamente che nello spazio ci sono le risposte giuste.
He decided to help us and participate in our meeting because he really believes that from the observation in space, they are the answer to many important questions, and therefore he make an effort to make the presentation as efficient and as possible.
Crediamo che innanzitutto siamo presenti in questo mondo e vogliamo esserlo anche in futuro, quindi se avete bisogno di di attività nella vostra nazione, noi siamo disposti anche, nel vostro continente, siamo disposti anche a spostarci.
And they are operative all over. Therefore, if any of you abroad in China or would like to use this technology, they will be happy to come there and help you.
Of course, because we have the whole network in the whole world.
Sì.
And
They're operative all over.
siamo presenti molto in Europa, ma stiamo sviluppando il mercato estero e crediamo tantissimo che nel cielo ci siano veramente le risposte, perché ho sposato questo progetto perché lo riteniamo veramente congruo con il nostro concetto di vita anche, oltre che di
Grazie.
lavoro. Grazie a
Grazie.
voi.
Well, they join us because they really understand the importance of our work. And he has followed, and he believes that the work we are doing all over is merit their help and their attention. And I'm really very, very grateful.
Thank you so much, Professore. See you.
Thank you to you.
You
Thanks.
too. Good work, good job.
Okay, thank you.
And it's really a fantastic difference between the traditional way and this very sophisticated, highly technological procedure. Thanks again.
Okay, thank you, Raymond. And now I'll move to Professor Zebin Su, talking about the Tianqin project.
Okay. Everybody, good morning. Thanks, Chairman, introduce and thanks organization to UME. I'm glad to introduce the International Center for Tianqin project. I'm come from Huazhong University of Science and Technology. My talk has the three parts. I will very briefly introduce the progress of Tianqin project on behalf of Tianqin Group. And then I will talk about the development progress of International Center of Tianqin. Finally, the summary. Tianqin is a space gravitation detection project independent proposed by China. And in 2014, Tianqin is officially proposed by Professor Jun Luo. And Professor Jun moved to the Sun Yat-sen University in 2015 as the president of university. And now, and then he created a new special research center of the Tianqin Center for study the Tianqin project. And now the Tianqin is led by the two centers. One center is the Tianqin Center in Sun Yat-sen University in Zhuhai, and CGE, our laboratory in Wuhan. Our laboratory is in charge of development of International Center for Tianqin. Tianqin is very special for another space gravitational detection. We chose is a geocentric orbit, and the altitude is about 100,000 kilometers. The three satellites form an equivalent triangle constellation. For its plane is linearly perpendicular to the elliptic plane, about 4.7 degrees. Is point to the calibration of the right drive the Plenary. Is compared with the NISA. Tianqin have a very short arm length. And that means we can choose is the high frequency, the sensitivity above the 0.1 Hertz, but also is a little worse sensitivity compared with NISA below the 0.1 Hertz. So that means with the higher challenging technology for Tianqin combined with NISA. And then I will talk later. Thanks to the choice of the geocentric the Tianjin contrasted with NISA, Tianjin have some advantage to in the engineer implementation, such as we have the faster launch and the transfer time, and also we can choose the stable of the consideration, and maybe it's too easy to precision. I use my one is okay. To the higher precision, the opt determination of satellite, and also is the satellite aggregation and the data transmission is easy compared with the NISA. However, is corresponding is because the gravitational wave choose the geocentric is studied less than before, so we should to study carefully about such as the Earth's gravity influence and so on. So Tianjin Center pay more attention to do some careful study of the possibility for the Earth orbital choice. Fortunately, up to now, we calculation and the Earth's gravity influence and the Earth's magnetical and the plasma effect and so on, we can't find anything can degrade the sensitivity of Tianjin in the intrinsic the frequency bound. However, it is noted that we have to choose the 3 months on and 3 months off the operation models, because we want to avoid the sunlight shedding with the interferometer. Nevertheless, we can add another set of the changing satellites to further with the detection precision. The route map of development of Tianjin project is classified Tianjin 0, 1, 2, 3, 4 steps. The number means the satellite used here. The Tianjin 0 and the Tianjin 1 and 2 are the key technology verification for Tianjin. And the Tianjin 0 and the Tianjin 1 have been successful tested before the 2020. Tianjin 0 means without any satellite, because we should to test the key technology to precision orbit determination for high altitude satellite, because it's 200,000 kilometers away, the satellite, the POD. So the Tianjin Center building a lunar laser range in Sui University Zhuhai campus. And then the absolute distance between the Earth and the Moon with accuracy better than 7 millimeter was realized in 2019. And Tianjin 1 means use one satellite to test the KO technology, such as inertia sensor and drag free control and so on. And then I will be talking about in detail later. Tianjin 2 means use 12 satellite to test the inter-satellite laser ranging technology for Tianjin. Was approved by our Chinese government in 2021. It will be launched in 2026. And the Tianjin 3 means is the final Tianjin project to detect the gravitational wave. We expect to be launched about 2035. And by the way, I will introduce is the two center. The CGE, the Center of Gravitational Experiment in our laboratory, is founded in 1983, is one of the earliest gravitational experiment research in China. Now we extended the research the field from the gravitational wave experiment into the ALM, precision management, geophysics, and the gravitational wave detection. Now we have the more than 16 63,000 meter square building and 10,000 meter square in care laboratory, and more than 120 the staff member, and more than 350 the PhD and the master study working here. Another center is Tianqin Center for Gravitational Physics. Was founded in 2015. Now they have finished the research building and the care laboratory and the lunar laser ranging station and the Tianqin ground simulation station. Now they are more than 17 the staff member and more than 200 PhD and master student working here. So the totally is the two center, maybe about 1,000 person working for the Tianqin project. And then I will introduce the development progress of United Center for Tianqin project. Before, I will talk about the requirement of United States development for Tianqin. As we know, gravitational wave will change the distance between two free-falling the objects. Even so, it's very so slightly. Even so, it's very slightly. So and then it make the one direction longer and another vertical direction shorter. So we can use interferometer to manage the gravitational wave singular. Is the principle. For the gravitational wave detection in space, I think we should use the develop three the fundamental elements. One is the lunar. We want to develop the higher precision interferometer to manage the harmonious variation. And the second one is the test mass. Test mass is regarded as the inertial sensor, inertial reference, and inside the spacecraft. It should be a free falling. So that means so-called inertial sensor. Third one is a spacecraft. Should be prove the small enough disturbance to maintain free fall, the condition, for the very stable the environment, the control the condition. Is the acceleration requirement of inertial sensor is the proportional to detection is the strain, the H, and the harmonious, the L, and the source frequency omega. Because the harmonious of Tianqin is shorter, so then we move the sensitivity, the frequency to the higher frequency. So it's compared with NISA, Tianqin choice is the corner frequency is 10 millihertz, compared with the 4 millihertz in Tianqin in NISA. So that the length range should be come to 1 picometer per hertz for Tianqin, but it's 15 picometer for NISA. And then is the acceleration should be the control within 1 times 10 to minus 15 meter per second square per hertz for Tianqin. Is 1 of the third of the Tianqin. So is the big technical challenge for Tianqin. We classified the inertial sensor research the 4 aspects. One is to do some research to parameter optimization and finish the system the design. And the second one, we want to develop the hydro technique for inertial sensor, including test mass and the electric house and the capacity of the sensor, the position sensor, and the electrostatic actuation, and the charge management, and the KG and the release system for the launch and the operation in orbit of the test mass. And the last one is vacuum chamber. Third one is we want to investigation and verify the design of the inertial sensor on the ground. We call it the performance test on the ground. In general, we should to develop the torsion pendulum to investigation some of the disturbance, such as the temperature, the residual gas damping, and the electromagnetic effect, and so on. Last one is to do some research to find the coupling of the inertial sensor between the other system, such as the interferometer and the drag free control and the spacecraft and so on. And then we can, based on the investigation, to determine how to determine the interface of inertial sensor with the other system. In our group, I study and developed the inertial sensor since 2001. I developed the torsion pendulum to test the performance of the capacitive inertial sensor. And we have finished the 5 inertial sensor flight model and successful applying to the 4 Chinese satellite missions. And now we have finished the disturbance management and the integrated inertial sensor for Tianjin project is ongoing the testing. And then we are detailed lately. First, I gave some of the noise model and requirement analysis of inertial sensor for Tianjin. The residual acceleration of test mass included 2 parts. One is the direct force fluctuation on the test mass, such as the temperature and gas and electromagnetic interaction and so on. Another is come from the stiffness coupling between the spacecraft and the test mass, the relative motion fluctuation. So we want to reduce the test mass, the direct disturbance on the test mass as possible, and then I will reduce the space and the test mass, the coupling, and also if the higher performance of satellite, the drag free control is required. Sorry. Thanks is the very nice design and the positive result of the inertial sensor for LISA Pacific. So we can heritage it is the very nice experience. For Tianjin, we should consider how to improve the 3 photo factors. Then in general, we can extend the mass, the massive, from the linear 2 kilogram for LISA to 10 to 2.5 kilogram. And then we are extending the electrical gap from about 4 millimeter to 5 millimeter. And we can reduce the electrostatic fluctuations. So we gave some very preliminary design of inertial sensor for Tianjin. In the first paper of Tianjin project, it published the CQG 2016, is limited by the residual gas damping at the 0.1 to 10 millihertz. And below the 0.1 millihertz is limited by the environment disturbance, such as the magnetic and the temperature effects. And about 10 millihertz is limited by the stiffness coupling. But anyway, we can give the preliminary design is satisfy the Tianjin requirement. And then we will to do to develop some kill technology and to prove that this design is okay. I will talk about the 3 kill technology development in our group. Firstly is the test mass. We design and manufacture the test mass with the gold platinum alloy. The mass is 2.45 kilogram, and the cube size, one length is 5 centimeter. Is the kill parameter of the test mass should to pay more attention the magnetic effect. So we manage it is magnetic susceptibility and residual magnetic moment by two methods. One, we use a torsion pendulum to manage the magnetic interaction, and another, I use the precise magnetometer to directly manage the magnetic moment of Tesla mass at a very near zero magnetic condition. And there is a grade very well. It is the susceptibility comes to 8 times 10 to minus 6. And the residual magnetic moment come to about 25 nanometer. It is better than the requirement for Tianjin. Second one is a capacitive with the position sensor. Sorry. Because we extended the gap. So, and also we should come to the same the position resolution. So we develop the capacitive sensor. In our group, we developed the capacitive sensor more than 20 years. Just now, we have finished the prototype of capacitive position sensor. And with the resolution comes to 2.3 times 10 to minus 7 picofarad per Luther hertz. It is 3 times better than the requirement of Tianjin. And the third one is the charge management. As we know, electrostatical disturbance is the main limiter of inertial sensor. The electrostatical disturbance including stiffness effect coupling and radial charge effect caused by the higher energy rays and the strial potential fluctuation. We said this effect is about 3 times 10 to minus 16 meter per second square per Luther hertz. It requires the strial potential fluctuation should be controlled within the 15 microwatt per Luther hertz, and the residual charge of Tesla mass should control within the 3.4 times 10 to minus 13 coulomb. So it is necessary to develop a long-touch method based on the photoelectric effect to precisely control charge of Tesla mass. A charge management control is based on the ultraviolet discharge technology have been developed in our group since 2015. We developed a micro LED with the wavelength is about 254 and the power is about 3 microwatts. And the lifetime is managed is better than the 5,000 hours. An engineer model charge management system is development, and its charge rate can come to 5 times 10 to 5 per second. ET per second. E means electrical charge. And also we test the performance on the ground using a torsion pendulum. It is the performance is 2 times better than the requirement of Tianjin. And then I will talk about how to test and verification the disturbance of the on the ground. As we know, the torsion pendulum is very sensitive to the force and the torque in the instrument on the ground. In our laboratory, in our center, we have more than 40 years experience in developing torsion pendulum and relative precision management, such as manage big G and equivalence pre-simple test and so on. And I used in 2001, I developed the single torsion pendulum, two-stage torsion pendulum, and free and electrostatic control torsion pendulum, and with the generate the constant fiber and use the high quantified 5 minutes of the fiber suspension have be the construction with a differential application, and then is the very useful for the test the performance on the ground for the inertial sensor. And also, I finished the investigation, the patch effect, magnetic effect, and gas damping effect in our group. And then we can give the serial analyzation and the experimental results, can modify the design and the requirement of inertial sensor for Tianqin. Due to the time limited, I just talk about recent thermal-induced acceleration experiment, for example. What we know, the temperature gradient effect is the mainly limited for inertial sensor, including the radiation pressure effect and the radiometer effect and the outgas effect. The radiation pressure and radiometer effect, we can estimate it, but the outgas effect doesn't give the estimation without model. We should to manage the by experiment because it depends on the material choice and its manufacture process. So in electrical house, the choice is based on the stable structure and no magnetic effect and no the thermal, the coefficient of expansion and higher thermal conductive and no outgas effect. For this choice is the momentum, but I think is the copper-based material maybe is a good candidate for electrical house because it is maybe is the TCE is worse than the molybdenum, but they have is much better the thermal conductive and outgas effect performance. So we we finished the experiment. Experiment result gives the temperature induced disturbance is about 16.3 times 10 to minus 17 meter per second square per node hertz. If the temperature graduation flag is controlled 5 microkilo per node hertz, as the design was the requirement in limiter. Based on the result, that means we can release the temperature control the requirement at least 4 times. This is a very good result. But anyway, we will do much more investigation in future. And then I'll give some of the talking, the Tianqin 1. Tianqin 1 is the first technology demonstration slide for Tianqin. Will be launched in December 2019. Is the main object to verify the dragonfly control with a capacitive inertial sensor and with a micronewton called gasless thrust. And another the care technology was verified, for example, interferometer, includes the laser, the optical bench, and the phase meter. The result is come to 13 picometer per node hertz. And this is the inertial sensor for Tianqin 1. Is very similar is the superstar is for the grace or grace follow-on. But we choose is a titanium material as a test mass. The mass is about 17 gray. And the capacitive gap is about 115 micrometer. The resolution is the verification on the ground comes to the 5 times 10 to minus 12 meter per second square per node hertz. And then we manage first I manage the non-gravitational force in orbit. The left picture showed is the satellite entering into and out of the sun shadow is the 1 or 2 micronewton. We can use very obvious management. And the middle, the figure is showed is the non-gravitational force of the spacecraft management in orbit by inertial sensor. In the flat direction, it comes to the 5 times 2 minus 11. And another directions is about 1 order the worse. And the right the result given is the longer direction measurement of non-gravitational force is the calibration with the non-gravitational model calculated by the GNSS and the Earth gravitational model is agreed very well. And then we can use the inertial sensor to calibration the thrust. The thrust used in the Tianqin-1 is the resolution of the thrust come to 0.2 micronewton per root hertz at 10 millihertz. And then we will test the drag free control. We switch off the electrostatic along the flight direction. And then thrust can be pushed the satellite to follow up with the test mass, and is very well. And based without is the drag free control comes 5 times 10 to minus 11 meter per second square per root hertz at 10 millihertz. Is much better the drag flow the performance, because we use the thrust with a small dynamic. But compared with Nissan, maybe it's 200 the gap, because which is limited by the net mass, just only 100 kilogram of the Tianqin-1 satellite. And the smaller control, by the way, just 0.2 hertz, and the very small capacitive gap. And now I have the design and the integrated inertial sensor for Tianqin project. And a titanium vacuum chamber have been developed. And the inertial problem and the vacuum chamber have been installed together. And the locking and release subsystem is being tested. This engineering model should be finished in the end of this year and will be tested in 2026 with the Tianqin-2 satellite. That one is a summary. The mission concept of Tianqin have been studied and is feasible. And the Tianqin-01 have been finished, are successful. And the care technology of Tianqin are being developed. And the design of Tianqin inertial sensor have been finished and almost verified on the ground. The care technology on inertial sensor included test mass and capacitive position sensor and the charge management are almost better than the requirement. And we have developed the flight model and successful applying in the for the satellite mission. And anyway, we will do more study. Okay, that's all. Thank you. Thank you for your attention.
Okay, thank you for your presentation. I can take just 2 questions. No, okay.
The science which is going on, not only. First of all, let me congratulate both members of the Chinese team. I am surprised of the extent of your work, and really is a splendid opportunity to have you here. Only a few years have passed, 3 years from the visit of Professor Luo, and I am really extremely impressed by what is going on. And just to say that and to allow Mr. Chairman to be conscient of this. And of course, you just arrived today. Therefore, it's hard for you to follow yesterday, but still try to
Thank you.
Okay, thank you.
Thank you very much.
Thank you for your remark. Okay, now I have time for one question, if any, because we are almost 20 minutes delayed. Okay, so thank you again, Dr. Zhou. And now we have Narika Sakarian talking about multi-messenger observation of blazars.
Good morning, everyone. Thank you. So I would like to present some recent works that we have been doing in Ikran, Armenia. So it's about how we use this AI, artificial intelligence, in research. So I will discuss very particular case that is for blazars. So, sorry. So this is the structure of my presentation. It's very simple. So I go from the past. So I speak what are blazars, why they are interesting. There are some unresolved issues. I come to present. I will discuss what the current multi-wavelength and multi-messenger observations are telling us. Then I will move to the future, how these machine learning or large language models can help to make better research, let's say like this. So this is, let me to introduce blazars. So in all the textbooks, you see that the basic definition of the blazars is that these are agents, quasars, which have the jet that is in the direction of the observer. And this is making a different nice features of this object. So, but these objects are very rare. So if you take all the possible candidates of blazars, you in different bands, optical, infrared, or X-ray, you reach around like 6,000 sources. If you compare with all the number of the galaxies that we know, this is very, very small fraction. So now the question is why these are interesting and why we are studying this object. So here I list some of the interesting properties of this object. So first of all, these are very powerful sources. So actually, these are most powerful non-explosive sources in the universe with a luminosity of 10 to 49 erg per second. The emission is produced from this relativistic jet, which is Doppler amplified. So it means that you can detect even very distant ones. And this jet is connected with the supermassive black hole. So if you study this jet, you are getting information about supermassive black holes. So, and so these are very powerful sources of multi-wavelength emission, and they are associated with multi-messenger observations. Of course, but one of the most interesting properties of this feature of this sources is the variability. So if you observe them in different bands, they have this very fast change of the flux in time. So here you can see on this left panel that the emission in all the bands is changing over time, and this can be very fast, so a few orders of magnitude in a very short time scales, in order of few minutes even. So even the blazars were an active topic of research for many years, but there are still some fundamental problems which are not yet clear. So this is connected also with the launching of the jet, how this jet is formed, how it is propagating, the structure, the composition, the acceleration mechanism. So what is the particles that they are producing the emission, and also the flares. So what is the origin of these flares that could go from time scales from years down to minutes? So these are all and some unresolved issues, which are the big part of the big puzzle. And the puzzle here is the blazar. So we need to understand all of these pieces to put them all together to be able to understand these sources. So and how we can do that, of course, to use these astrophysical messengers. So if we put in diagram all these messengers, so these are gravitational waves, photons, cosmic rays, and neutrinos, and they are this very wide range of frequencies going from gravitational waves to neutrinos and cosmic rays. And if you just plot here, if you consider the first messengers, that is our photons, and if you just plot here the spectrum of blazars, you see these are filling all the electromagnetic range. So you can use all of these observations in different band to study these objects. What means to study? It's this, you have this beautiful data that is shown on the left here down. So you have all of this data collected in different bands, and you want to understand what is the origin of this emission. So according to the current models, you have this compact region in the jet, which is moving very compact because it comes from the variability constraints. So if you have a very short time variability, it means that it's coming from a very compact region. And you are observing this emission, which appears with this double peaked structure. So now the question is, what is the origin of these peaks? So the main theories we can divide in two large groups. So the first one is the leptonic models. According to leptonic models, this emission is produced from the electrons. So we have the injection, acceleration of the electrons that are injected in this emitting region. They are cooling, and the first peak corresponds to the synchrotron radiation, while the second peak is due to the inverse Compton scattering of internal or external photon fields. In the past years, these models were very successfully applied to model different emission states of the sources. So you have this active and normal state. You can just derive the parameters and you can understand why you have these flaring activities. So these models were taking into account the location of the emission region. So even you could have some external fields that they are contributing to formation of your spectrum. But what is good, but that in the few recent years now is possible to study blazars using these other messengers, neutrinos, thanks to the observation by neutrino instrument. So this window here now of the neutrino window also is open for blazars. So it means that together with this extensive multi-wavelength data, you have additional information which is coming from neutrinos, which is good. Why? Because you can make a better job in your models. You can investigate these sources in more details. So if you have neutrinos that they are produced from with the photons, it means that you are dealing with the hadrons. So with electrons, you cannot produce ultra high energy neutrinos. So this is why in these scenarios, together with electrons, you have injection of the protons as well. So again, the first peak of this spectrum is because of the synchrotron radiation, while the second peak is now from the contribution of the protons. This could be direct proton synchrotron radiation, or could be secondaries that are produced from this electromagnetic cascade that is developing when the protons interact with the photons. So in this case, you have now your spectrum look like this. So you have these two components in electromagnetic spectrum, plus you have the information that is coming from these neutrino observations, which is good. So then you have more information to build your models. So just to show blazars as a multi-messenger sources, so this is gamma ray sky map from the Fermi observations, while these white ellipses, these are the uncertainty regions from the IceCube observations. So you can see some of them are overlapping with the direction of some blazars. And of course, these all multi-messenger studies, they started when there was this observation of this famous blazar, Texas 05 or 506. So there were many different theories trying to explain what is the origin, how the neutrinos are produced. Of course, I'm not going to discuss the details here because this was a very hot topic in the past few years. But I want to mention this is not the only case. There are some other blazars that are also in the associated with neutrinos, which is interesting, and all of them are very interesting objects. But in particular, I would like to speak about this source on the top, on the left. So it's PKI 0735, which was mentioned also on Monday by Lipunov. So what is interesting in 2021, December, there was a signal observed by IceCube detector for some neutrino event, which is 172 TeV, which is not an exceptional because there were more energetic neutrinos observed. But what was interesting, because after the announcement by IceCube, another 3 neutrino instruments also reported observation of neutrinos from the same direction of the sky. So usually in neutrino astronomy, astrophysics, they are dealing with single events, but then you have a multi instruments that they are detecting event, which is very interesting. And if you look the uncertainty region of this IceCube event, you see that there is a blazar which is close to this region. So let's see what is happening with this source. So this is the multi-wavelength light curve of this PKI 0735 in gamma ray, X-ray, and optical UV band. You see that there is nothing so exceptional happening. There are some small flares, which is normal because we are dealing with blazar. But this is just before the neutrino observation. So the time of neutrino observation is marked with this red line over here. And you see that in all the bands, the source was in a highest possible flaring state when the neutrinos were observed. So if you zoom this part, you see these 4 different colors. We show the arrival time of different neutrinos. And you see that the source was super bright in all the band. So in the X-ray band, it was so bright that you could also see variability between different snapshots by Swift telescope. And this is why it was very interesting to study. And of course, we collected a lot of data and we performed some modeling with these hadronic scenarios to see how these neutrinos and electromagnetic radiation could be produced. So if we move further, so what is the status of the current models? So all of these observations, they provided a very significant amount of data. So we have a lot of information about their emission spectrum, about variability, about polarization, or etc. So how these models work, they just use either leptonic or hadronic. You select some period of the observation, you model this data, or 1 or 2 periods, and you try to understand some some of the parameters of this object. But of course, this is a very oversimplified picture, because since they are changing over the time, to see just one moment period of the emission, this is not enough. So to demonstrate this, this is the multi-wavelength spectrum of this blazar in 3D plot. So it's like one axis is the time, frequency and flux. So you see that over the time, there is the change. So the question is, if you just model one period or just two periods, is it enough to understand these sources? And of course, the answer is no, because the data is much richer. There is a lot of information that we can just extract even from already existing data. And how you can do that is, of course, that you try to model as many as possible simultaneous data that you can accumulate for a single source. Plus, it is important that you do proper modeling. Proper modeling means you have to build very detailed model, the numerical, everything included inside. Plus, when you do the fitting, it should be not just by eye fitting, but you statistically need to obtain these parameters. What is the, so this is what I just explained. So you have the injection of the electrons in the jet. You have this, how this injection, this is the simple case. So you have the electrons that they are emitting, cooling over time. You need to follow what is the evolution of these electrons. Then you build the corresponding emission spectrum, and you need to compare this with the data. As soon as you do these things, you get information about your source. But this seems super easy, but in technical, this is not that simple. The problem is this optimization of the parameters. So you can do in the two different ways. So first you do this regular normal fitting. You just take your numerical model, you put in these fitting engines, and you wait very long time. Another way is you compute this table model. So you compute for a large number of parameters, and then you try to make the interpolation. But of course, both have some challenges, some problems. In the first case, if you want to do really a nice job, you need to do 10 to 4, 10 to 5 times you need to compute the Likely loop, let's say. So if you have a numerical code for a single set of parameters, this would require, like in the simplest case, like 30 seconds of running time. It means if you do the fit for 10 to 4, 10 to 5 times, it is really very long time to wait. So you can wait some days, then you get your result. But if it is not good, then you have nothing to do. You have to repeat. Instead, if you do the table model, you are dealing with very big files. So then it's not so easy to every time to interpolate or do something. So of course, what you could do is just try to make your model faster, so you can make some approximation. So move from fully numerical to semi-analytical, but it's not so good because you could gain like factor of 2. So instead of waiting like 30 days, you wait 15 days, which is still very long because you cannot do anything in that time. So this is where this progress in this artificial intelligence can help us. This is how, because these models are known to be very effective when you are dealing with the large volumes of data. They can help you to do better job in the analysis. They can find some patterns that humans are not able to find because it's too complex. And they can do everything more faster by making it automatic. So if you could just do it, then you are free to do some other research. Of course, there are some problems with these models also, which are listed here, but I'm not going into details. There are some problems that you need to take into account when you are dealing with these ML models. But just let me to show some example how you can implement these ML models in your research, that it will be under control, all the challenges. So let's say you have the blazar that you want to understand the emission from these sources. So I'm just selecting two different scenarios. So the first one is synchrotron self-compton. The second one is external inverse compton. And I just show how you build your neural network here. So you know, in both of your models, the number of the free parameters. So in the first case is 7 parameters. In the second case is 11 parameters. And you know the range of the parameters that you are interested. So this is very important. You consider very wide range of parameters. You don't need to concentrate only to those that are physically reasonable, but you need to have a very wide range of parameters. Then in this wide range of parameters, you just do some sampling of the parameter space. There are some techniques that you could do that. You select some of these parameters and you put in your numerical code. In our case, we use Soprano, our code that was developed in 2 years ago. So you put all of this in your numerical code and you start to generate data. So for all of this parameter space, you are generating some data. As soon as you generate this data, then you can apply the traditional method, etc. You can train your neural networks on your data. So what means to train on your data is basically you try to map the input parameters that in your case are your model-free parameters with the spectra. Spectra means the radiative signature of, let's say, electrons. So as soon as you train, now you have a model that is linking your input parameters with your output, or the output is your case is the spectrum of the emission. So in our case, we did with the convolutional neural networks. These are very nice, powerful tools that can be applied also for time series analysis. I'm not going to present the details here because I invite you all of this afternoon in the session and I talk by Damian Begue, which will explain the structure, details about how we build this network and what is the structure of it. But I just want to, after you do this training, you get some neural networks that they are able to reproduce the radiative signature of electrons in a very wide range of parameters. Then you can use these neural networks to perform a fit. Why? Before it was not possible to make the fit, and now it's possible because initially with the numerical code, you had the time for 30 seconds for single parameter space. And now with these neural networks, it's much faster. It's 0.04 seconds for the same parameter space. So you have a factor of a lot changing the time. So now you can just put in the fitting engine, and this is one of the results that we obtained. This is Markarian 421. You see the red line is the best model, and while on the right you see the posterior distribution of the parameters. So you can do this with as many blazars as you like. When we developed this CNN, we understood that it would be very useful that this is available to everyone, not to only us, but to everyone who wants to can use it. So you decide to make it publicly available, but not in the traditional ways that you put in something in GitHub and you ask you have to install this in your computer, then you can use. No, we made it with some platform that is our data center, called Markarian Multi-Wavelength Data Center. So what you do, you come to the database, there is session of theoretical modeling, you just upload your data that you are interested. This is interactive. Then you put the redshift, then you put your email, and you press the button of the fit. And everything is happening in the background. You get some email saying that your analysis is being processed. Then you do your job, whatever you want. So in some 15, 20 minutes, you get the second email saying that your data are ready for review. You just open, you go, you are redirected to the data center web page where you see the fit result. You have the best parameters. You can download the posterior distribution, etc. So it gives you the chance to really do a nice study of your sources. And if you remember in the beginning, I mentioned that you need to model as many ACDs as possible to have a better understanding of these sources. This is just to demonstrate one single example. So this is this Blazar OJ287. On the right side, we show how different components are changing over the time. And from here, we selected many simultaneous ACDs. We put it in our fitting engine, and we see how dynamically this radiation is changing in time. So these are 800 periods of the time of modeling, which took like a three half day of fitting. So it was super fast. And on the top, on the left, you see how the radiation is changing over time. And on the right, you see the parameters how are changing in time. So you can just make a very nice study to understand what is the origin of the flares, which was the changes in the sources, etc. So in the last few slides, I would like to speak if these new changes in the last year, these large language models or generative AI, they can help in the research or not. So this is about this ChatGPT that is very famous in the past few months. So everyone is speak about that. So the question is, can these large language models or generative AI help in the research? So the answer of this is yes. Why? Because there are a large amount of data that the information that is available every day. So this is beyond the possibility of the humans to get this information and to investigate. So this is why these large language models can help, but not in this form. Why not in this form? Because all these available large language models, they are trained on a very large number of parameters. So if they have a lot of parameters, then if you want to have a specific application of these tools, they are giving very broad answers, or sometimes they are giving some errors, or it is called hallucination. So it is hallucinating because it finds some wrong patterns and gives you some answer that is nonsense and is not reality. So these are some issues that you have to think about that and to try to solve. Well, there are some ways that you can overcome these challenges. So first one is fine-tuning. So I believe on Monday, Wang Yu was mentioning a few things about this fine-tuning. So you can do the fine-tuning as on the parameters. But there is another method which is faster and it works and is easy to do, is this retrieval augmented generation, RAG. So how this works? So for this, let me to introduce this Astro LLM, what we are building just now. This is the large language model for astrophysical research that can help with the research. So we believe that this should be like an assistant, so it can help you with your research, provide you some information, etc. So this Astro LLM should have specialized knowledge on astrophysical this terminology. So it should be trained on astrophysical articles. It should have access to the multi-wavelength data. It should have the access to the advanced modeling techniques. It should be able to help you to interpret your result. And of course, it can have also an educational purpose. So it could be used for educational purposes. So how we do that is very known technique. It's not so simple, but it's known technique. So you take all the articles that are about the PDFs that say about astrophysics. You split them in a text format, then you split this in a chunks. So you have some paragraphs, text, or etc. Then you put them in a vector space. Vector space because you need to have all the symbols should have some direction, some order, or etc. So when some people, the user in this case, is asking you a question, you just don't immediately answer. Your large language is not answering the question immediately. What is happening? It comes to this vector space, tries to find the context that is related to the question. Then it passes to the large language model, which in our case is the ChatGPT, which is trained on all the data of the internet. Then when it passes the query plus the context, it gives you the answer, which is exactly about your question, which is more details, and it is, you avoid to have this hallucination or error. So to just demonstrate this, we were just first selecting the extragalactic astrophysics and specifically blazars, because we know about blazars, so you can judge if the results are correct or not. So just to show, here is an example. This is like the platform that we are working now. So we are checking something. So on the left side is the ChatGPT. On the right side is this Astro LLM that we just built, train it on the, not all the articles by blazars, but a few of them. So if we ask the same question to these two ChatGPT and Astro LLM, so I ask a very specific question about an ice cube event, which is very narrow and very specific. You see that ChatGPT is giving some very wrong, very general, but very wrong answer, while the other one is giving you very specific about the energy, the source that is associated, some more details. If you ask more, what is the origin of this emission from this blazar? The ChatGPT gives you very general answer that this is blazar, so it comes from the jet or etc. Why the other tool is providing you some very detailed information that it is modeled by hadronic scenarios, where is the interaction, etc., etc. So this is very helpful because it can help you all to, if you have some problems, that it can really help you to get information on several of your questions. So this is not the only functionalities. We are going to implement some further options, so we will give them access to the multi-wavelength data. So if the user asks, get the ACD of this source, just it goes, gets the data, plots and returns to the user. But if user wants, so it can make just an advanced modeling and return you the answer. So you can sit in front of your computer, you have the access of the data, and you have access of the modeling tools. This is not just a wish list, because we are able to do this because we have, in the past years, we were building this Markaran multi-wavelength data center, which is a platform where you have a lot of data. This is archival data plus the data that we are analyzing almost every day. So in our server, this is running automatically. So it contains a large amount of data for almost all blazars. So if you, for example, if you just type a name of the source that you are interested, you can retrieve this data in a very, now you see the spectrum. So you see this is in all the band from radio to gamma ray bands. You have a very detailed information. So this will be accessed to our chatbot. So if the user asks any data, you can really retrieve the multi-wavelength data from here and provide to the user. And of course, it will also be able to make modeling with the neural network that I just described a few slides before this. So if this is conclusion on the future directions, so if you remember in 1970s, the astrophysical data was sent by post in the magnetic types. No, there was not so much data, but now we have this exponential increase of the data that is beyond of our capabilities to model them or to analyze them. So we need to have these machine learning models to help. And of course, astrophysics is the research that will really benefit from this because there is a lot amount of data. For will be our next steps is to make available this neural network also for the multi-messenger modeling. So the data is already in training. So I think in 2-3 weeks, we will have this data, this available as well. We want to apply the same methodology for the other sources. For example, the first model for GRBs is under computation. So very soon this will be also available. We can try also other sources. We want to add all these functionalities to AstroLLM to include all the data for all the information for blazars. Plus, we want to extend them to have also different disciplines of astrophysics. So this will be an assistant that can help you with your research. So this is my last slide, and I would like to show this conference that we will organize in October. So I want to invite all of you to join us in Yerevan, which will be in October, from in the beginning, the first week of October. Thank you.
Thank you, Narek, to stay inside the time. It's not a credit soon.
Welcome.
One question from.
Thank you very much for the nice talk. The neutrino message has revealed which of the two possible models, leptonic or hadronic, is the most favored one. And a second question, if I may. So isn't there a risk that we stop modeling theoretically if, all we do is look at what the AI is going to give us in terms of what it has built out of some models?
Thanks for the question. Yes, the first question about hadronic or leptonic, in reality, all these messengers, this data that we are getting, they are showing that leptonic models are more favorable, but with the subdominant contribution of the hadronic component, which is popping up in the X-ray band. So if you look proton synchrotron model, that is more, there was thinking to be most likely one, then you end up with a very large luminosity of the jet. But if you have a leptonic scenario that the hadronic is just contributing in the X-ray band, so you get some upper limit, this model seems to be more effective and they are producing the answer to this neutrino event. For the second question, that is true, because if you are building the AI on the information that you are providing, and if you don't provide very broad information, that you are limited. But the problem, the point, if you try to make very broad different models, and you could have this AI that is trying different models or different judgment, maybe it would be better also for us, no? You are able to model on different scenarios, then you can. The important that we should judge the result, not the AI. So AI should do the work for us, like in normal cases. So AI is doing the job, is giving us the results. Then the humans, we need to judge which modeling or which result is more physically realistic or not. I don't mean that we need to give all the power to AI, because in that case, we are risking to face some difficulties, but it should be like biologically guided artificial intelligence, because we need humans, we need to really guide what is the given the output by AI.
More question? Yeah, there.
Just curious to know, then the ChatGPT model you have, it depends on the amount of information you're fed in, right? So what year range have you covered in your, in the ChatGPT model, you have the vectors which are coming from the inputs you have fed in. So I'm just curious to know what age range of references and documentation have you covered, and because it has to keep it updated as well to give you it, right? So could you just give a few sentences on that? Yeah, thank you.
Well, thanks. Actually, this is a very interesting question. First, we are trying to just build on the Blazar publication. So we select all the Blazar papers that have been reviewed, not just prod settings, only the ones that have been passed the referring or they are published. So if you look in NASA IDS, you have around like 17,000 something number of papers about only Blazars. The question is how frequent we can just update this information. If you do fine tuning, this is very expensive to redo every time, because if you do fine tuning, it takes time, plus it takes money to do the things. But this thing, regularly you can update even every week, because this doesn't cost anything. You just update your vector database. So if you build on data or paper, let's say until now, in 1 week, if you wish to update this data, it would be very simple. You just need to add these additional papers that you are interested, and it go to your vector space, and your model can work this with new context as well. So this is the advantage. This is very widely used in these private sectors because they are feeding information that they need, and they can use this method. And this is the advantage of this one, that you don't need to every time train these large language models on the new parameters. You can just fill the context, and these large language models are looking the information from this context. This is why it is better to use this method.
Okay, thank you again, Nareka, and let's move to the next speaker. Dr. Ashtekar. Oh. Okay, in the meantime, I have a question for you. I was impressed by the user-friendly interface that you have shown. You think we can apply that to, for example, photometric classification like curves of supernovae, because we have hundreds of objects per night with LSST. I cannot imagine to follow spectroscopically all those. Because of succedere.
Just while we are waiting a moment, don't forget that we will have an extra talk at the session end this afternoon, because Rainer Genzel is going to be connected just before the conclusion of today's session.
Can you hear me?
Yes, yes. Okay.
Okay. I would like to share my screen. Can I share the screen?
Yes.
Yeah.
Please go
Can
ahead.
I share the screen?
Yeah.
Okay. Sorry. Can you see my screen now?
Yes. You have 25 minutes plus 5.
Okay. Wonderful. Wonderful. Thank you so much. Okay. So I first of all would like to begin with the apology that this talk is really not about multi-messenger astronomy at all, but it is really about quantum gravity. And the reason for that is that the organizers asked me specifically to talk about quantum gravity. I could have given another talk altogether, but this was the request that they made. So let me start. And the main topic here is really about exploring the nature of quantum geometry that is created by quantum matter. So this is a work that is done with several people, not just me, but I initiated it, and also there is a summary that you can find in a paper that was written about 18 months ago. So let me start with setting the stage here. And the point here is that we have a question which has to do with experiments and trying to explore the quantum nature of gravity through experiments. So the interface of quantum information and quantum field theory and quantum gravity, it is emerging as a forefront area of fundamental physics. But because concepts emphasized by the two communities, namely quantum information community and quantum gravity and quantum field theory communities, they differ, there is much debate currently about what exactly the proposed experiments, and these are experiments of the type that were proposed by Bose et al. And by Marletto and Verdal, what can they hope to accomplish? And much of the debate can be traced back to the difference between what we would like to call as a Coulombic and what one would like to call as radiative aspects of Maxwell fields and Einstein gravitational fields. And the debate comes from this following, that if I look at the Hilbert spaces of states that we normally use for photons and for gravitons, they are made up of radiative degrees of freedom. In the case of gravitons, transverse traceless degrees of freedom. And and if you just have, there's no information about the Coulombic interaction directly. But when matter is represented by quantum fields, there are also, obviously, just because of the Coulombic interaction, the space-time is curved and so on. And the question is, are these Coulombic modes also quantum mechanical in nature? Some people have advocated that no, only the transverse traceless modes are quantum mechanical, and the Coulombic interaction is really classical. And the reason for this is because in the photon Hilbert space and the graviton Hilbert space, we don't see any Coulombic information. And so what I'm going to do is to present an exactly soluble model to answer this question. And the answer is going to be yes, the Coulombic information is also genuinely quantum mechanical. So the first example, in order to give this a sharp meaning, I will consider a classical theory, which has in fact no radiative degrees of freedom at all, only Coulombic degrees of matter. And then we can look at this Coulombic degrees of freedom of the gravitational field would be created by some quantum matter. If you have quantum matter and creates this Coulombic degrees of freedom, then what we'll see is that the geometry actually has some surprising quantum features. And then I will just quickly summary. And the main point is that Coulombic degrees of freedom really are quintessential quantum properties. They do have those properties, and they are inherited from the quantum properties of matter. And it really, however, needs a non-perturbative treatment for this, and the non-perturbative treatment has certain surprises as well. So to set the stage, let us consider the following. We can look at the example I'm going to consider is not directly physically interesting, although four-dimensional cylindrical waves in four-dimensional space-time really satisfy the mathematical properties of this example itself. So this example is really gravity in 2 + 1 dimension. And the reason is because here the coupled to matter, because it provides a near ideal setting. And the reason is that now there are no gravitational waves. So it's a really sharp distinction. There are no gravitational waves. The entire gravitational field is Coulombic. And so we can ask if, in fact, the gravitational field exhibits any quantum properties, especially because in this example, one does not even have a Hilbert space which corresponds to gravity. So the theory is particularly simple because in 3 space-time dimensions, G times M is now dimensionless, and that means that there is no scale which will set, which will tell us when the gravitational collapse occurs to form a black hole. In 3 + 1 dimensions, if you pack matter in a radius GM, in a radius which is the Schwarzschild radius, inside that, then that would become a black hole. But here we do not have such a scale. And the second thing is that this model is exactly soluble if you add one symmetry. So because of these simplifications, one can analyze this model in detail, and one finds that even though there is no Hilbert space for gravity, space-time geometry and the gravitational field have genuine quantum effects. So this is a bit surprising. So what happens is that there are operators which correspond to gravitational degrees of freedom, Coulombic degrees of freedom, or the metric, if you like, is an operator, but it is an operator on the matter degrees of freedom. And although we do not live in 2 + 1 dimensions, this theory is useful at a conceptual level. Furthermore, we'll find that it exhibits genuinely non-perturbative quantum effects. There are similar ideas and similar experiments that one can perform in 4 dimensions, but though they become a little more technical, and I cannot explain them in the short time that I do have. So let us consider now the system. So it really is a 2 + 1 gravity GR, so 1 time and 2 space dimension, coupled with a scalar field. So scalar field satisfies this Klein-Gordon equation, and then we have the Einstein's equation, which says that the Einstein tensor is given by 8 pi g. This is a 2 + 1 dimensional g times TAB. And since there is no gravitational collapse, we only have scattering states, and they lead to some interesting and unforeseen properties. Now, there is an interesting fact in 2 + 1 dimensions, namely, there is a duality between Maxwell theory and scalar fields. I can take the gradient of the scalar field, as I showed up here, and from that construct a Maxwell field using the antisymmetric tensor epsilon ABC. And then it turns out that if the scalar field satisfies the Klein-Gordon equation, if and only if FAB satisfies the Maxwell equation. So we cannot tell if, in fact, physically we're looking at a scalar field or a Maxwell field. The Maxwell field in 2+1 dimension has only one polarization, and that is encoded in the scalar field, if you like. So this is a nice duality, and more surprisingly, the stress energy tensor of the scalar field, which has very different form from that of the Maxwell field. But if I use this definition of the Maxwell field that is up there on the slide, then the stress energy tensor of the Maxwell field is exactly equal to the stress energy tensor of the scalar field. And so you can say that I'm either in a Einstein-Klein-Gordon system or Einstein-Maxwell system, and it is useful to go back and forth these two pictures. So the experiment I'm talking about is really just shining light. As you see up here, the light is going up there, but it is now in 2+1 dimensions. So think of the vertical direction as being time and the horizontal directions as being space. And once this light is shot, what happens is that this is a matter field which is going to curve the space-time around it. And that is and we're going to perform experiments in the vacuum region around the matter field and test if, in fact, the gravitational field created by this quantum matter has quantum degrees of freedom. So just a couple of facts about this about this model. The system that I've written down, either the Einstein-Maxwell or the scalar field Maxwell, is still quite complicated, but it becomes exactly soluble if you restrict yourself to situations in which there is an axial symmetry or a rotational symmetry. So in that case, the norm of the rotational symmetry gives us a radial coordinate, and you can write down the metric in an unambiguous manner. This is, you completely fix the coordinates, so that the metric says dt times dt squared minus dt squared plus dr squared plus r squared d phi squared. And since two-dimensional metrics are conformally flat, you can just write down the two-dimensional metric factor by the flat two-dimensional metric factor times conformal factor, which is just e to the g times u of rt. And then the statement is that Einstein's equations will tell us what this unknown function u is. So the only free function is u in a stationary axisymmetric model, and that is going to be determined by Einstein's equation. If u is equal to 0, then of course the metric is just a flat metric written in the polar coordinates. And now, if I look at the wave equation satisfied by the Klein-Gordon field with respect to the physical metric, it turns out it satisfies this equation if and only if it satisfies the equation also with respect to the flat metric. So to solve the Klein-Gordon equation, I can just forget about the physical metric, which is not known to me, and I can just use the fiducial flat metric and solve the Klein-Gordon equation. And then the solution is just given in terms of Bessel functions and e to the I omega t. And then I know, because of the general fact, that since it satisfies the Minkowski, the wave equation with respect to the Minkowski metric, it also satisfies it with respect to the curve metric for any u of r and t that you give. But now Einstein's equations are used to determine this u of t. And then it tells us that this u of r and t, this function of two variables, is just the integral from 0 to r of the energy in the scalar field, but with respect to the Minkowski space. So I start with the fiducial Minkowski space, solve the Klein-Gordon equation in it, and from the solution, I can construct what this u of r of t is. And then the statement is that my Klein-Gordon equation in the flat space implies that it also satisfies the Klein-Gordon equation in the curved space, and its energy density determines for me this u factor. So I have an entire complete solution to Einstein-Maxwell theory. And if all the matter is contained, for example, inside a circle of radius r0, then u of rt is just the total energy of the scalar field for all r bigger than that r0. So now what does the space-time geometry look outside in just classical theory? Well, let's just examine the metric outside, because that is totally uncontaminated by matter. So if we establish some quantum properties of the geometry outside the sources, then there is no question that it really refers to the gravitational field, because the matter field is just zero there. So then, therefore, this U is just given by the Minkowskian energy of the Klein-Gordon field. And GTT and GRR are just given by this constant, namely e to the g times the total energy in that scalar field. So this is a clean experiment to test the Coulombic, test the Coulombic gravitational field and see if it is actually quantum or not, because as I said, it is uncontaminated by matter. So what I can do is I can actually, outside the sources, outside the sources, the space-time geometry is locally flat, but globally it is not flat. And it is like a conical singularity. And therefore, what I can do is perform an experiment. I can take a spinner and go around the source, but always remaining in the vacuum region. And when I do that, the spin actually, the state of the spinner actually changes by a rotation. And this rotation is kind of the double cover of the Lorentz group in 3 dimensions, which is SU11 rotation. So the spin actually rotates, and you can measure that. And that rotation of the spin, this is the experiment, and you measure the rotation of the spin, and that has the information about the total energy, in the ADM mass of the gravitational field. More precisely, the bottom equation shows you that the ADM energy, which is E of the curve metric, is given by a non-polynomial function of the energy of the scalar field in Minkowski space. So it is interesting that you've got a non-polynomial function coming there. And this phase rotation I've talked about, this trace of UC, is completely determined by this energy. So if I measure how much the spinner has rotated, then I have done a measurement of the energy of the system in Einstein Klein-Gordon or Einstein-Maxwell theory, because they are dual to each other. And so I said, note that this E is actually bounded above, even though the Klein-Gordon energy, H0, goes to infinity. So it really is, the fact here is a very clear example that full nonlinear general relativity tames the theory in the ultraviolet. The energy is unbounded without gravity, but with gravity, the total energy is bounded because the gravitational interaction has a negative energy. And then this is a genuinely non-perturbative effect, because if I do a perturbative expansion of this energy, I will get infinitely many terms. At first order term, you just get unbounded, but sum of all these terms is actually bounded again. Okay, so now that brings us to talk about the quantum gravity experiment. So quantization has been carried out systematically using the Hamiltonian methods. And since the degrees of freedom lie in the scalar field alone, what we can do is to just quantize the scalar field in Minkowski spacetime, because the scalar field satisfies the wave equation in Minkowski spacetime is equivalent to it satisfying the wave equation in the curve spacetime. And then I got the general solution. So we just replace the coefficients by the annihilation and creation operator as usual, and we have a quantum field. The gravitational operators, this is the key point, that the gravitational observables now are operators on the matter Fock space. In other words, if I now look at the metric, for example, metric becomes quantum mechanical because the scalar field is quantum mechanical. Here, for example, in the middle of this transparency, I have written down the equation for GRR, and that equation is an operator, but the operator is really this H0 hat, which is the energy of the scalar field in Minkowski space. So it is really on the matter Fock space that the geometry operator acts. And what we are going to do is to consider the point number 1 here, that I put this quantum field in a coherent state, because it is as classical as possible, if you like, peaked at a classical solution F phi naught, and therefore this coherent state is given by the formula I wrote down there. So this is a state which is sharply peaked around a classical source, classical solution, and it has minimum uncertainty in the scalar field and its conjugate momentum. And then we can also look at the energy of the H0 up here, which is in the bottom, of this classical field with respect to Minkowski space, and you can calculate the expectation value of the energy, and you find that the uncertainty is extremely small, goes as the minus 1/2 power of the expected number of, so to say, Klein-Gordon particles or photons in this coherent state, and is totally negligible when n is much bigger than 1. But now we look at quantum geometry. So I just mentioned to you that the components of the metric are now operators on the Fock space. So I can take this coherent state and calculate the quantum geometry. And I get some answer. But the important thing is that this answer has an H bar explicitly sitting everywhere. If I were to do a power series expansion here, to first order the H bar cancels, I get the classical result. But there are big quantum corrections sitting there all along. So even though the state of the matter field is semi-classical, is a coherent state, it is not really the expectation value of the metric operator on it carries quantum properties. And in particular, the right-hand side differs from the classical value because of these H bar factors all over the place. Now I'm talking about two interesting features which are in the black, namely the difference between the classical expectation values and between the classical value and the quantum expectation values is non-perturbative in the Newtonian constant. And GH bar, which is the Planck length in the 2+1 world, it provides a new scale. But in Minkowski space, in quantum field theory, G is equal to 0, so I don't have a new scale. And similarly, if I were to consider, so there is no length scale there. But now when I bring both G and H bar together, I got a length scale. And therefore, I can talk about, in the quantum theory, I can talk about a Planck frequency or Planck length and so on. And now what we can do is to calculate the expectation value of GRR, take this laser beam to be sharply peaked around some frequency omega naught, and I can calculate the expectation value of the GRR. And what you see here immediately is that you do get a classical value, but it is multiplied by an exponential factor. And therefore, it really is not classical at all. If I measure this expectation value, I will cleanly find out the deviations from the classical value. And this is true both at low frequency as well as high frequency. And with high frequency photons or the scalarons, H bar remains even in the leading term. And in fact, as the expected number of photons increases, the matter coherent state becomes more and more classical, but the geometry operators have larger and larger fluctuations. And that is a subtlety here, namely, if you look, there is a new scale that requires G, namely GH bar, Planck length, or 1/GH bar, the Planck frequency, but it refers to the frequency of the quantum matter. So this new scale now refers to the frequency of the quantum matter, but it does not affect the fluctuations of the quantum matter itself. But interestingly, it exponentiates those fluctuations in the gravitational field. The precise nature of Einstein nonlinearity is such that small fluctuations of matter field get exponentiated in the geometrical field. So therefore, the statement is that it's clear that we do have quantum effects. The GRR, the space-time metric, is really a quantum operator. It exhibits fluctuations that could actually be measured by performing this thought experiment, or in which you take a spinner and go around to calculate how the spin state changes. Classical theory would give you one answer, and quantum theory would give you quite a different answer. So let me summarize. Full non-perturbative 2+1 general relativity provides an arena, a very nice arena, clean arena, to explore the quantum nature of the Coulombic interaction, because there are no radiative modes in this system at all. Since there is no radiative modes, there are no gravitons, and we don't even have a Hilbert space associated with the gravitational field. Therefore, at first, it is very confusing as to how can there be quantum nature of gravity. Well, it turns out that the geometrical operators, like the energy, like the ADM energy, or like the metric coefficients, those are quantum operators, but they act on the Hilbert space, on the Fock space of the matter fields, of the quantum matter fields. And still, quantum matter field introduces strong quantum effects on the gravitation observers, as I just said. And even you can do this experiments, these measurements outside the sources. So there is no contamination. There's no direct transfer of knowledge of quantum nature of matter to gravity. It really is through just Einstein's equations. And it is really the Coulombic interaction that is doing it. And matter is in tame coherent state. The specific nonlinearities of Einstein's equations greatly magnify the quantum nature of gravitational observables, which are represented by operators on the matter Hilbert space. And the Planck frequency made available by both G and H bar introduces a new scale in the quantum matter. Nonetheless, the quantum properties of matter are insensitive to it. They don't know anything about this new scale, but the quantum properties of the Coulombic gravitational observable are extremely sensitive to it. So although we do not live in 2+1 world, conceptually, the model provides a clean evidence that the Coulombic interaction is also quantum mechanical, and the BMU type experiment can directly probe the quantum nature of the Coulombic part of the gravitational field, but not the radiative part. And as I mentioned, that there are also similar experiments, thought experiments that I sort of come up with to check the Coulombic properties in 4 space-time dimensions, but they are much more subtle. They have to do with angular momentum and so on, and therefore I did not discuss that. Thank you. I think I just finished in time.
Okay, thank you so much, Professor Ashtraker. I have a question here.
Yeah.
Well, beautiful presentation, and I think I feel relieved because when we introduced the Klein-Gordon field in general relativity, in my work with Brunazzola, which gave origin to all the work on boson stars, we are safe, apparently. And this is a good news. Thank you.
Yeah, it is. It is. Yeah, you did a physically very interesting thing.
Yeah, another one here.
Hi, thank you for the talk. I wanted to ask, because usually gravity or quantum gravity in 3 dimensions is dual to Chern-Simons theory, and you quantize it like this, but somehow there's no trace visible of that observation in your calculation. So I understand coupling the scale of it destroys this duality, but
right.
I would expect
exactly.
I would expect that there should be a limit. For example, if they make the scalar field very heavy, where it decouples and you see traces of that, but there's nothing of this kind of visible here.
No, because I mean that does not have direct. I mean, by doing this, but you know, perturbation around large mass, I cannot really cleanly see the Coulombic aspect. That's why we did not do it that way. But you are absolutely right. If there is no scalar field, then this theory can be just put in the Chern-Simons form. That's absolutely right. Yeah.
We have one more question.
Okay.
Thanks for your talk, but I have a question about the vacuum state. Can you define in your Hilbert space the vacuum? And if so, is it dependent on
so thank you. So the statement is the following, that in this model, in presence of axial symmetry, the scalar fields, first of all, we put the degrees of freedom in the scalar field. So the Hilbert space is a Hilbert space only of the scalar field. And furthermore, since the scalar field satisfies the Klein-Gordon equation with respect to the physical metric, if and only if it satisfies that equation with respect to the Minkowski metric. And as a result, we can just use standard Fock quantization of the scalar field in the 2+1 dimensions, and the vacuum state is a standard Fock vacuum. If you like, is a coherent state peaked at the 0 Klein-Gordon field.
Okay, thank you. And is there a difference between the local observer and the external?
Yeah. So the statement is that if I have observer inside the matter field, that would be the local observer. Then, of course, there are more. I mean, we have worked it all out, but then the test is not so clean because there the effect is determined not just by gravitational field, but also by the quantum matter field, which exists in that local region up here. So, so that's why you can do all this, the analysis of the, looking at GRR, the metric components, or GTT, the metric components. We can do all that analysis also locally inside the matter field, but then that is, I mean, inside the matter field, there are also fluctuations of matter field itself and so on that are coming in, and it's not easy to cleanly separate. Whereas when you're outside, there is no matter field at all. If you like outside, and then the state, and nonetheless, you've got these fluctuations. So it is a very clean test for the quantum nature of the gravitational field.
Okay, thank you.
You're welcome. Thank you.
The last question.
Okay, so maybe just ask you when you compare the Einstein equation with the Max equations, we know the electromagnetic interaction is governed by the symmetry of the charge, the symmetry of charge of electrons. But the general relativity is governed by the symmetry of geometry. So how could you compare to these interactions? I mean, these basic two forces.
Yeah. Right. So what I'm looking at is two theories in which there is only gravitational field and the Coulomb field, and the electromagnetic field, and gravitational field and a scalar field. There is no charged. I'm not looking at Einstein Maxwell charged field system. I'm only looking at Einstein Maxwell system. So if you like, in the Einstein Maxwell system without charge, what we have is just free electromagnetic waves. They're not created by sources. It's just, as far as Maxwell field is concerned, it is source free Maxwell field.
So actually, all matter fields should also have a gravitational interaction. Why the gravitational interaction?
Absolutely. So this example chooses a very simple setting in which you can separate, and we can test the quantum nature of purely gravitational interaction without worrying about the matter one. So this is a very special example is to address this particular question, to give a very clean test. So if you have other matter fields, yes, there will be similar analysis, and we know how to do that, but then I don't have a clean test.
So my question, why people don't think about the gravitational interaction is also related to the symmetries of the matter. It's not just from the geometry.
Yeah, so here the matter, the scalar field or the electromagnetic field also has symmetries of matter, of axis symmetry. So it also has that symmetry, right? So it's not just the metric which is axis symmetric, it's also the Maxwell field or the scalar field. That's also axis symmetric. So everything is axis symmetric. All fields are axis symmetric.
Okay. Thank you. Thank you so much, Professor Ashtekar.
Thank you.
Okay. We are 10 minutes later, so I propose to meet again 11:40 instead of 11:30. Okay. Enjoy the coffee break. Okay. Take a seat, please. We started the second part of the session on multi-messenger astronomy with Sarah Vigeland talking about gravitational waves with pulsar timing arrays.
Well, repetita iuvant. I would like to remind you that tonight, after the parallel session finish at 6 o'clock, there will be here a talk by Reinhard Genzel at 6:30 before the conclusion of the meeting at 7 p.m. Therefore, please come back here at 6:30 in this room.
How do I advance the slides? It doesn't sorry. All right, thank you, everyone. Thank you for inviting me. This is my first time attending the Marcel Grossman meeting. I am Professor Sarah Vigeland from the University of Wisconsin-Milwaukee. And it's been really great to hear all of these talks and learn about all of the exciting research going on in gravity and relativistic astrophysics. I'm going to be talking about gravitational wave astrophysics, which is really a new field. I mean, really quite new. LIGO ushered in this new field not even 10 years ago now with the first observation of gravitational waves from merging binary black holes. And since then, they've observed many, I've honestly lost track, gravitational wave events from compact binary mergers. But LIGO is only able to see high frequency gravitational waves, so things with frequencies of hundreds of hertz or kilohertz. And astrophysical and cosmological sources are emitting over many orders of magnitude, same way they do in electromagnetic radiation. And so just as we need different kinds of electromagnetic telescopes, we need different kinds of gravitational wave detectors. We heard about some of these types of gravitational wave detectors this morning. I'm going to be talking about something that's way down here at the low frequency end, pulsar timing arrays. There are many sources we can expect to find there, we might find there, but the primary sources we expect to find are supermassive binary black holes. And we've heard a number of excellent talks at this meeting about supermassive black holes. We know they are common in the universe. We know that all massive galaxies have them at their centers. And when two galaxies merge, those black holes will come together and form a binary. Now, for me and my colleagues, we're interested in them when they get to this point. They are at sub-parsec separations. The orbital periods are months to decades. And when they're in this regime, they are emitting gravitational waves with frequencies of nanohertz. Okay, the frequency evolution is very slow in this regime. They evolve very little over a human lifetime. So we often call these continuous waves because for the simplest case of a circular orbit, you can just think of it as emitting a single frequency, kind of like a single note. Now, all of the supermassive binary black holes in the universe at subparsec separations are going to be emitting these gravitational waves, each one at some frequency determined by its orbital separation and masses. Okay, and the superposition of all of those gravitational waves from the population form the gravitational wave background. So this is kind of a hum of gravitational waves from a cosmological population. Okay, now you can actually show analytically that if you have a population of circular supermassive binary black holes and they evolve only due to gravitational wave emission, the characteristic strain spectrum should follow a power law that goes like frequency to the -2/3. Okay, but this is just on average. Any kind of real astrophysical population is going to have some small deviations from that due to the fact that you have a finite number of sources. So for example, in this plot here, which is showing the result of an actual simulation, right? You can see at the high frequency end, there's these little spikes. That's just because in this particular simulation, there's maybe a few extra loud binaries down there. So you get this breakdown from the power law. But as we go to lower frequencies, it's much smoother. That's because you have more sources contributing. Okay, so how do we detect nanohertz gravitational waves? Now, this idea goes back many decades. Estabrook and Wahlquist in 1975 wrote a paper where they calculated the Doppler effect of a sinusoidal electromagnetic signal induced by gravitational waves. And that's the effect that we use in pulsar timing arrays. Okay. Sazin and Detweiler in two papers in 78 and 79 first proposed using pulsars to detect nanohertz gravitational waves. And they also suggested that these may come from massive binaries. Hellings and Downs in 1983 provided the crucial insight that the signal that you would see in your pulsars would be correlated between two different pulsars. And they calculated this correlation. They showed that it would follow a pattern, which we call the Hellings and Downs curve. that depends only on the angular separation between the two pulsars. And this is key. This is how we know we're seeing gravitational waves and not something intrinsic to the pulsars themselves. They also placed an upper limit on the gravitational wave background using 4 pulsars, not one that is now, competitive with what we're able to do with a lot more pulsars, but still a very interesting proof of this method. We've heard a lot of talks about pulsars, so I don't think I need to explain them in too much detail, but pulsars are rotating neutron stars. They emit these beams of radio waves. And for pulsar timing arrays, we use this special subpopulation, millisecond pulsars. So these are pulsars that have been spun up to much higher rotational speeds. They rotate hundreds of times per second. And this happens because they accrete material from a companion star. Okay, that's how they get the extra angular momentum that they need. And these, the first millisecond pulsar was actually discovered in 1982 by this group of people led by Don Backer. And millisecond pulsars are really crucial for making this work because they are much more rotationally stable than canonical pulsars. And Backer also was the one who coined the term pulsar timing array. Okay, so pulsar timing, oops, okay, hang on a second. Okay, that's fine. Pulsar timing is the process by which you measure a series of pulses coming from the pulsar, okay? And you measure their arrival times, and then you fit them to a timing model that has to describe everything about the pulsar and the pulse's propagation through the interstellar medium, and then everything that happens in the solar system as they're passing to the telescope. Okay, so that's how we learn about these pulsars and their properties with such high precision. Most of our millisecond pulsars are in binary, so you have to take into account the orbital motion of the pulsar. They have to propagate through the interstellar medium where the free electrons cause dispersion. And then, of course, the Earth is orbiting the sun. The Earth is rotating. We have to take into account all of these effects. So this is my little cartoon for how I think about a pulsar timing array. You have your pulsars, hopefully more than 3. Each one has its own timing model, its own white noise, and its own red noise. So the timing model encodes everything about that pulsar, its spin period and period derivative, its binary motion, etc. Then, of course, there's white noise. This could be radiometer noise, so it depends on your telescope, or it could be something intrinsic to the pulsar itself. And then finally, you have red noise, which is an astronomy term for noise where you have more power at low frequencies than high frequencies. So things are varying more on long time scales than on short time scales. And this could be caused by spin noise. So maybe the pulsar is wobbling a bit as it's spinning down. Now, all of these effects, these 3 here, are going to be unique for each pulsar. But we do have some common sources of noise, most of which come from things happening in the solar system, because of course that's the point in common. We're observing all of them from our solar system. So for example, if there's some kind of clock error, that's going to show up in all of your pulsars. Okay, the solar wind, right, can affect multiple pulsars in a particular way. Okay, and then finally we have the gravitational wave signal. Okay. So the signal that we're looking after is this. So the signal in the residuals is the S here, okay? And it's the integral of the redshift induced by gravitational waves. Now the redshift we can divide into 2 parts. There's the part that's proportional to the gravitational wave itself. That's the delta H term that I've written there. And then there's this geometric term, the F. We call that the antenna pattern. That's a geometric term that basically depends on the relative position between your pulsar and your gravitational wave source. Okay, so it's going to be different for all of your pulsars. Okay, when we actually calculate this out, what we end up with is 2 components of this signal, one which we call the Earth term, one which we call the pulsar term. So the Earth term is basically what is the gravitational wave doing at Earth? The pulsar term is what is the gravitational wave doing at the pulsar? And all of the pulsar terms are different because the pulsars are at different points in the sky and they're also at different distances from the Earth. Okay, and so this T sub P, that's the time you have to correct for the light travel time between us and the pulsar, right? So you're actually seeing the gravitational wave at a different point in time. Now this is for a single binary here. If we want to consider a gravitational wave background, we just have to integrate over a whole population of individual binaries. And when you do that, you end up with this correlation curve on the right, which is called the Hellings and Downs curve. So the correlation between two pulsars will be maximum if the pulsars are closely aligned. Then as they get to be about 90 degrees apart, they become anti-correlated. And then as you move them even further apart, they become correlated again, but the correlation doesn't go back to the same maximum as if they were aligned. Okay, so this blue curve here, that's what we call the Hellings and Downs curve. That's kind of the fingerprint of gravitational waves. Okay, now the Hellings and Downs curve, deriving it, actually relies on the fact that in general relativity, there are only two gravitational wave polarizations, the plus and the cross. But in some other theories of gravity, there could be additional polarizations, up to 6 total polarizations for the most general metric theory of gravity. And so by measuring the correlations and seeing exactly what they look like, you can actually put constraints on the presence of alternative polarizations. You know, pulsar timing arrays are really good for this because we have so many different lines of sight between the pulsars and the Earth. Okay. We also look very closely at the correlations because some of these common sources of noise that I mentioned earlier also induce correlations, but they don't induce Hellings and Downs correlations. And so by measuring the correlation, making sure that it's Hellings and Downs and not something else can help you be certain that what you're seeing is gravitational waves and not some form of noise. So for example, a clock error. If there's something wrong with our time standard, it's not perfectly uniform, right? That's going to induce the same signal in all the pulsars. So the correlation would be 1 for all pulsars, regardless of their angular separation. On the other hand, the solar wind induces a dipolar correlation. So it goes like cosine of the angle between them, okay? So that's how we can distinguish between some common sources of noise and gravitational waves. Now, there are a number of pulsar timing array experiments active around the world right now. Okay, I'm a member of NanoGrav, which stands for the North American Nanohertz Observatory for Gravitational Waves. We have members around the world, but we're primarily based in North America, and the telescopes we use are all in North America. Okay. We're also joined in this kind of research by the European Pulsar Timing Array, the Chinese Pulsar Timing Array, the Parkes Pulsar Timing Array, the Indian Pulsar Timing Array, and the Meerkat Pulsar Timing Array, using this collection of radio telescopes. And we all are part of a consortium called the International Pulsar Timing Array, through which we share our data and our methods. So after we construct our own individual data sets, we pool them together and make one giant IPTA data set. This is really important because it allows us to get higher cadence observations of our pulsars because we're using all of these telescopes. It also lets us see more pulsars. You might notice there are only two of these telescopes are in the Southern Hemisphere, Meerkat and Parkes, right? So they're able to see pulsars that the Northern Hemisphere telescopes just can't see. Okay, now I'm going to primarily talk about the NanoGrav results, but all of the pulsar timing array collaborations published results last year showing evidence of a Hellings and Downs correlated process. So when we analyzed the NanoGrav 15-year data set, we found that the data preferred a process with Hellings and Downs correlations versus one without, with a Bayes factor of 226 in favor of correlations. And what I'm showing here are the reconstructions of the correlations. So on the left, it's a reconstruction using the Bayesian analysis. So it's binned by angular separation. And on the right, it's actually an independent pipeline using a frequentist method, which is called the optimal statistic. So they agree well with one another, and they also agree well with the theoretical prediction, which is the black dashed line. Now, in order to understand the significance of our detection of correlation, we have to construct a background distribution for our detection statistic, either the Bayes factor or the optimal statistic SNR. Okay, we do this by basically augmenting the data to scramble the the correlations that are present. So the noise remains, but there's no correlations anymore on average, okay? We do this with a process we call phase shifting. So when we do that, and then we compare to our actual measurement, we find that the false alarm probability of our measured Bayes factor is about 10 to the minus 3, and the false alarm probability of the optimal statistic SNR is between 10 to the minus 3 to 10 to the minus 4. So that gives us 3 to 4 sigma significance. Now, in terms of the spectrum of this signal, we're seeing a correlated signal that extends over many frequencies. And that's how we know this is a gravitational wave background and not gravitational waves from an individual binary, which would produce gravitational waves primarily at a single frequency. Okay, so the signal that we see extends from about 2, which is the lowest frequency we can probe, all the way up to about 28 nanohertz. Okay, and I'm showing the reconstructed power spectrum here. So the gray violins are showing the power at each frequency, making no assumption about the underlying power spectrum. And then the blue line shows the reconstruction if you do assume that it follows a power law like I was showing on the earlier slides. The dashed black line is if you assume a power law and you fix the spectral index to the spectral index predicted for circular supermassive binary black holes. Okay. Now, last June, Nanograv, the EPTA, the NPTA, the PPTA, and the CPTA all coordinated the publication of results where they all presented evidence for Hellings and Downs correlations in their most recent data set, and that's what's shown here. So the plot on the upper left is a joint EPTA and NPTA data set. So they combined their data together to make one data set. Okay, then we have the results from the PPTA. Those are the green violins. And then we have the results from the CPTA at the bottom. They used a different detection method than the other groups, which is why their plots look quite different. Okay, so this is really exciting to see. It's good to see all of the results in such good agreement. Okay, especially because it's worth pointing out, a lot of these groups are using different pulsars, right? And we're also using different methods, right? And yet we're all seeing this correlated signal, which is consistent. Now, as the IPTA, we published a joint paper where we compared the power spectrum found by the EPTA, NPTA data set, the Nanograv data set, and the PPTA data set. And again, we see good agreement between them. We see that they are broadly consistent with one another. Although I would point out that the power spectra that all of us are seeing are still, there's still large uncertainties. That's because we're really just starting to see this signal. This is still very early for us. The next step is what I talked about, creating a combined data set that's going to combine data set from all of these groups, plus a few extra groups, actually, to make the most sensitive pulsar timing array data set that we've ever created. Okay, so what does this tell us about astrophysics? So I wanted to just return to this cartoon to remind you of what we're talking about when we think about supermassive binary black holes emitting nanohertz gravitational waves. They're kind of in that middle panel, that second panel. They're orbiting one another relatively slowly. The orbit is evolving, but not too much. And the orbit is primarily evolving due to the emission of gravitational waves. But in order to get to these subparsec separations, we know that environmental effects must play a part. This is the famous final parsec problem, right? If you just rely on gravitational wave emission, they won't make it to subparsec separations in a Hubble time. So environmental interactions must drive them to get closer together. And so it's possible that at really large really large orbital separations, which corresponds to the lower frequencies that we're able to probe, that we are seeing that their evolution is being driven by environmental effects. Okay. So these are the results of some simulations that actually generate populations of supermassive binary black holes and then figure out what the gravitational wave background should look like. Broadly speaking, the amplitude is most sensitive to the mass distribution of supermassive black holes and the galaxy number density. So like how often do galaxies merge to make binaries, okay? The shape is what tells you about the mechanisms driving the binaries to merge. Is it just gravitational wave emission, or do environmental effects play environmental effects play a role? And if they do, you see this kind of bend in the spectrum where you go from being environment driven to gravitational wave driven. Okay. Now, all of these astrophysical properties here that I'm listing, these are things that we already have some idea of from electromagnetic observations. But this is the first time we're able to say something about them from gravitational wave observations. So this is a form of multi-messenger astrophysics. I think of it as population multi-messenger astrophysics. Now, it's still early days in terms of being able to really precisely characterize the power spectrum, but we can say that the power spectrum we're seeing is consistent with a population of supermassive binary black holes. There is some preference for models that include environmental interactions versus ones that only involve gravitational wave emission. The amplitude is on the higher end of what theorists had been predicting, which is, I think, pretty interesting. But supermassive binary black holes aren't the only possible source of this signal. There's any number of new physics models that could produce nanohertz gravitational waves. At this point, we're not able to rule those out or to differentiate between some of these new physics models like cosmic strings or phase transitions and supermassive binary black holes. But in principle, with future data sets, we'll be able to measure the power spectrum more precisely, and we'll be able to do this because all of these models make different predictions for exactly what the gravitational wave background power spectrum should look like. I just want to close by talking about prospects for detecting individual binaries. If the signal we're seeing is coming from a population of supermassive binary black holes, it's likely that we will see a small number of individual binaries within the next 5 to 10 years. But there are a lot of uncertainties on that time frame because it depends a lot on where the source is located on the sky. Our sensitivity is not uniform across the sky. If you take a source with the same parameters, you just move it around, the signal to noise ratio of that source can vary dramatically, making it go from detectable to non-detectable. And that's another argument for why the IPTA is so important. With more pulsars, better sky coverage of them, you get better sensitivity across the entire sky. Okay. We're already using our data sets to put constraints on some of these candidate binaries that have been identified from electromagnetic observations. So for example, HS1630 is a periodic quasar. So you see the light curve here, it has this periodicity, okay? And we can use our data sets to put constraints on the properties of a binary if it is actually a binary. Now, right now, the constraints we put they're not very competitive. But again, with future data sets, we will be able to say something interesting and either determine that this is a binary or put constraints on the mass ratio. Okay, so to conclude, pulsar timing array collaborations last summer published the first evidence for a gravitational wave background at nanohertz frequencies. So this is the beginning of nanohertz gravitational wave astronomy. With longer observing baselines and more pulsars, we think we will be able to detect gravitational waves from individual binaries and hopefully make multi-messenger observations of binary AGN. Right now, what we're all working very hard on and very excited about is preparing the next IPTA data set, which will contain about 120 pulsars with data from all of the collaborations I've mentioned, plus the Meerkat pulsar timing array, CHIME, which we heard about in Vicky's talk, and LOFAR. And this data set is going to be the most sensitive data set we've ever produced and give us much better measurements of the gravitational wave background. Thank you.
Thank you so much, Sarah.
Thank you, Sarah, for your presentation. I have 3 quick questions. and 3 quick answers, please.
Thank you. That was very nice. You mentioned environmental effects. Can you elaborate on what they are and what is the impact over pure gravitational waves?
Yes, so environmental interactions could be interactions with a disk, like a disk of material, but it could also be stellar scattering. And both of these cause the orbit to shrink faster. It loses energy faster. So with stellar scattering, for example, you're like throwing the stars out, right? And so the binary shrinks faster. And so that's why environmental interactions produce this turnover. You're like depleting the number of binaries at these separations because they spend less time there. Yes, it can be quite dramatic.
Hi, so what's the status with detecting gravitational memory in this nanohertz frequency range?
Oh, that's a very good question. So yes, we do searches for gravitational wave memory. But unfortunately, to be honest, the rates of memory events from supermassive binary black hole mergers is not great because the rates of the mergers themselves are not great. But of course, gravitational wave memory is just like a generic prediction. So there's still the possibility we could find gravitational wave memory from some other kind of event. And we do, I mean, it is one of the primary searches that we do perform.
Well, this is the third time that we find exciting news in this field. On the day we started, we had a very nice presentation by Andrea Possenti, who is working also on this topic. And China, of course, we gave them an award because in the long range, I think also the fast radio burst could play a role in that if they are able to extend the data to higher Z. Therefore, I want only to add my congratulations for your work and keep going.
Thank you.
Just curious, if you happen to detect one of these individual supermassive black hole binary mergers, would you be able to know which direction the signal is coming from and how far away the signal is?
That's a really good question. In terms of the direction, the sky localization depends a lot on what part of the sky it's in. If it's in a part where we have a lot of pulsars, good news. If it's not, bad news. But even in the best case, we're not going to get great localization. There's still going to be many possible host galaxies. So we're actually working on methods to try to identify the host galaxy given some kind of sky localization region. In terms of the distance, it is possible actually to measure the distance independent of everything else if you can measure the frequency evolution of the binary. And I said they're not evolving very much over human lifespan, and that's true. But the light travel time between us and the pulsars is order 1,000 years. So if the evolution is even a few nanohertz over 1,000 years, you can actually measure the chirp mass independent of other parameters, and then you can just calculate what the distance is.
Thank you for the talk. So I want to know, how do you calculate the massive black hole mass function from the merger rate? So you use simulations for the halos where the supermassive black hole are hosted, or you use semi-analytical approaches?
That's a great question. So I know some of my colleagues do it analytically, but in Nanograv, we've created a software which we call holodeck, and that's based on simulation. So you populate these galaxies with supermassive black holes, you evolve them to subparsec separations. So it's simulation based. Yeah.
Yeah, thank you for the nice talk. I had a question. You mentioned that with Nanograv, you see between 3 and 4 sigma, depending on which way you analyze this. And then you showed us the others see something similar and then you combined it. I didn't understand what is the significance once you combine all the data. That would be sort of a bit more the quantitative way of saying how much the others support the same result.
That's a very good question. So right now we're still making that combined data set, so we don't know. But based on what the work we've already done, we expect the significance to be much higher just with the data that we already have. You can kind of estimate it by just taking the pulsars and analyzing them all together, but you can do better than that because we do observe quite a few pulsars in common. What we're actually doing is we're taking all the observations made with all the telescopes of a given pulsar, making a single really long high cadence data set for that, right? And then putting that into the gravitational wave analysis. But that process takes a lot of time because you have to, it's a lot of work to try to match all of these observations made with all these different telescopes. But we do expect that the significance will be much higher in IPTA DR3.
Okay, Sarah, it is a pleasure to listen to you, but we have to stop here. So, Marta Coleoni, where are you? Thank you.
So thank you to the organizers for the invitation. I am Marta Coleoni. I am giving this talk on behalf of the LIGO Virgo Cabra collaboration. And I'm just going to walk you through a bit all of the analysis and searches that the collaboration has been performing. As Sarah nicely explained, we have several instruments covering different parts of the gravitational wave spectrum. And we are covering the last part here, say between a few hertz and order of kilohertz. And the nice thing of having different detectors covering adjacent frequency bands is also that there are prospects for multi-band observations. Here on the right, I placed a plot where you can see some tracks of stellar mass black hole binaries that are going to start off in the LISA frequency band, and then they are going to merge in the LIGO band. And this could be very interesting for determining the properties of these sources more precisely, and also for performing tests of general relativity, for instance. So we are sensitive to various potential sources. Usually we distinguish between short duration and long duration. Roughly short duration, by short duration we mean, say, fractions of seconds to hundreds of seconds. And long duration signals are the ones that we expect to observe continuously throughout all the observing runs. Short duration can be also modeled and unmodeled, and the distinction there means that for the first category, we have templates, and we think these templates represent quite accurately the signals that we're going to observe. And these are the events that we have observed so far, and I will touch upon this point later. Then we have a modeled short duration events, and under this group we put gravitational wave burst. This could come from events for which we don't really have accurate and templates. They could be core collapse supernovae or emissions from magnetars, or even phenomena related to cosmic strings. Then we have long duration continuous waves, and the classical source for this type of signal is gravitational wave emission from spinning neutron stars with some non-axisymmetric deformations, plus other more exotic sources that I will mention later on. And finally, we have stochastic background. Okay, so this is a summary of the international network of ground-based gravitational wave detectors. We have 5 operational interferometers right now, the 2 LIGOs in the US, GEO 600 in Germany, Virgo in Italy, and Kagra in Japan. GEO and Kagra had a brief joint run in 2020. The sensitivities of both Kagra and GEO 600 is much lower compared to the other instruments. but this was an important test bed to make sure that Kagra was ready to go, essentially. And Kagra was supposed to join the current observing run, but there was an earthquake, unfortunately, in January this year, and the operations got a bit delayed. LIGO India was approved by the Indian government, but the construction is yet to start. So I guess we will see it in the next decade or so. So what are the advantages of having multiple detectors for us? Multiple detectors means better source sky localization. And this is very important for electromagnetic follow-up. Another advantage is that we can constrain better the gravitational wave polarization. And in particular, we can also check for the presence of non-tensorial polarizations through a technique called null stream. So the more interferometers we have, the more alternative polarizations we can test. Then we also have, well, the issue of duty cycle, in the sense that the interferometers are not always online. And so if you have more instruments, you're sure that if one is offline, then you have others that are actually working. And finally, we see signals better in the sense that they have more signal to ratio if we can sum up the individual signal noise to ratio of more instruments. So this is a summary of the observing runs that the instruments performed. The network performed already 3 observing runs. And now we are in the middle of 04. So what happens in between these observing runs? While the instruments get improved, there are a lot of improvements, say, to the test masses, to the optics, to the way quantum noise is handled with frequency dependent squeezing being introduced recently. And this allows us to detect more and more events per time, as it's shown here in the bottom right plot. So you can see that the sensitivity has been increasing constantly since 01. And in terms of detections, the first 3 observing runs racked up 90 confident detections. And here we have some preliminary numbers. These are from late June of this year. So we have more by now. But for O4A, we had 81 candidates that will need to be confirmed in offline follow-up. And for O4B, we had 34. So in total, we have already more than 200 potential events. Okay, so how does the online search for these triggers work? Well, we have several pipelines. We have some pipelines that rely on match filtering and on template banks. But we also have pipelines that are sensitive to unmodeled signals, because as I said, we could have signals for which we don't have actually gravitational wave templates as of now. And these other pipelines relying on looking for excess power clusters, say, correlated among detectors. Then we also have multi-messenger pipelines like Raven that searches for coincidences between gravitational wave candidates and external detections of astrophysical events like bursts or neutrino bursts. So a very nice thing of the gravitational wave network is that we produce public alerts. So as soon as one of the pipelines gets triggered, there is an early warning alert that's sent. And right now, for binary neutron stars, we can send alerts several seconds in principle before the merger time. So we can see in a way, the merger before it happens. And this is because for low mass binary systems like binary neutron stars, the detectors can accumulate enough in a signal noise ratio even before the merger, because we can see many, many gravitational wave cycles of the order of 1,000 for binary neutron stars. And so what happens then is that there is a chain of alerts. At some point, there is human vetting because the instruments are not perfect. Sometimes there are glitches, there are instrumental artifacts that are really powerful, and they could be mistaken for signals. And that is why human vetting is very, very important. And if everything goes fine, then the initial alert is confirmed with a GCN circular. Otherwise, there will be a GCN retraction. And as you see here on the top, we have some significant detection candidates that have a false alarm rate below a certain threshold. But then we also have a more lenient threshold that results in many more low significance detection candidates. And these are also published because we want to enable electromagnetic coincidence searches. So I mentioned at the beginning that more detectors mean a better sky localization. And here I just wanted to show you an example. In particular, we have that during O4B, Virgo is being used for the sky localization in the online analysis. And here I just compared two events. One was from O4A. It was observed, well, it was localized only by LIGO, Hanford, and Livingston. And it was the best localized candidate in O4A, but still the 90% credible area was 80 square degrees. Whereas you can see now here an example from O4B, this is another binary black hole candidate. And here with Virgo, we achieve a 90% area of just 20 square degrees. And we also have some better localized events than these. So this is quite impressive. So then here, I just wanted to show you a bit the reach in terms of redshift that the current instruments have, and also in terms of distance. So here on the left, there is a plot showing you the in-spiral detector range in megaparsec. This is a conventional measure of sensitivity, so it would be the average distance at which an equal mass 1.4 solar mass BNS could be detected with a signal ratio of 8. And you can see here that, well, for the two LIGOs, we're around 160, more or less on average, megaparsec, whereas Virgo has a much lower range, around 50. And on the right, there is a plot that you must have seen already here at the conference, where you see a comparison of the reach in terms of redshift for both binary neutron stars and binary black holes. So you might notice that the two ranges are not the same. This is because for gravitational wave detectors, more massive events are more luminous, so we can see them further away. And you can also see that future third generation detectors like Cosmic Explorer or Einstein Telescope will really push quite far the maximum redshift at which we can observe these sources. And right now, the maximum redshift that we observe with LIGO are around 1. So here is a summary of the family tree of all the binary black holes that the collaboration have confirmed so far. So this is the 90 confirmed detections that we had after the end of O3. And finally, we managed to observe all the possible so-called canonical binaries. So we observed binary neutron stars, binary black holes, but also black neutron stars. And in red and yellow, instead, you have the observations coming from the electromagnetic side. And you can see that in general, gravitational wave detectors tend to see more massive events. This might be related to an observational effect because, as I said, we are more sensitive to more massive and therefore more luminous events, but it could also be that we are actually probing different stellar environments with different metallicities. So this is an event that I'm sure all of you know by now, was the first binary neutron star detected back in 2017. And this was our first and last, for the moment, multi-messenger event, but hopefully we will have more in the future. It was the first joint detection of a gravitational wave signal, but also electromagnetic counterpart. There was a short gamma ray burst, just 1.7 seconds roughly after the merger, detected by Fermi integral. And also there was a kilonova detection with observations then going on for years of the afterglow. These electromagnetic observations allowed also to identify the host galaxy and redshift, and this was quite important for enabling more precise estimates of the Hubble constant, for instance. But it's also important, it was also an exceptional event in terms of the constraining power for tests of general relativity, for instance. The constraints on the dipole radiation that we put with this event are still the strongest, and they still beat even the combined events that we computed with all of the binary black holes at the end of 2003. And finally, this event represented a very strong observational link between BNSs and short gamma ray burst. So other very nice things that we can do with this event are the following. So we were able to put constraints on the tidal deformability, as shown here on the right upper plot. So this plot is essentially showing that this observation disfavored very stiff equation of states. Then, as I mentioned, the combined determination of the luminosity distance at the redshift allowed for a quite, well, compared to gravitational wave standard, quite competitive estimate of the Hubble constant, though not competitive clearly with other measurements that I will show later. And also, this observation combined with the kilonova observation gave us a lot of information on the structure of the jet power by BNS mergers. There was a long discussion regarding the exact nature of the merger, with one of the best hypotheses being that of a structured jet. And then we had another confident binary neutron star detection a couple of years later. This was interesting because the total mass of this system was much higher than the total mass that you would infer from galactic binaries. And while there were various explanations as to why this was the case, so again, we could be probing different information channels, but also there was also another hypothesis of this event being the result of a fallback supernova episode, where essentially the second helium star doesn't spin up the first neutron star, and it manages to stay more massive, and then it accretes matter through the fallback mechanism. Then, as I mentioned at the beginning, we had some neutron star black hole binaries events. These two were the first detections or unofficially announced. And despite the fact that there was a neutron star in these systems, as it was the case also for the second binary neutron star, we didn't manage to place significant constraints on the tidal deformability. This was not surprising, because given the parameters of this system, we expect only weak tidal effects, because the mass ratio was quite unequal. The effective in spiral spin was roughly negative. And these are all factors that go against having significant tidal disruption. For some neutron star black hole systems, in fact, you have signals that very much look like BBH signals. Just you could tell them apart essentially in the ring down, because they will have different quasi-normal modes frequencies. And this was the latest event that the collaboration announced. It was GW 230529. This is another potential black hole neutron star, although again, the fact that the second mass is a neutron star is not coming from any direct inference on the tidal properties, but just on the mass and spin properties. But the main interesting thing about this event was that the primary fell inside what is called the lower mass gap, where some models of core collapse supernova cannot actually generate remnant. And it's also a range of masses where we don't have observations of X-ray binaries that would suggest that this gap is actually filled. So this is very interesting because this can also inform simulations of supernova core collapse, as we heard in Chris Fryer's talk, because this tells you that this gap is not empty, and it could give information, for instance, to the people doing numerical relativity simulation of supernova core collapse. And again, the SNR of this event, the signal to noise ratio, was modest, and as I said, we don't have constraints on tides. Then we had some other notable binary black holes. The interesting thing here that I wanted to highlight on the right was that there was a counterpart proposed for the most massive event, 1905-21. For a long time, like, people were not really expecting, I guess, counterparts from binary black holes, but this was supposed to be a merger in an AGN, although the association has not been confirmed. Then, as I mentioned, after compiling the catalogs of transients, we perform a lot of tests of general relativity. We test really a lot of things: the presence of black hole mimickers, existence of massive graviton, local Lorentz invariance, violations, and so on and so forth. And until now, we have not detected statistical significant deviations, so we can just place upper bounds like the ones showed here on the possible deviations in the post-Newtonian coefficients of the phasing. Then a few years ago, the collaboration also started performing gravitational wave lensing analysis. Again, so far, there were no claims of confident detection of gravitational wave lensing. But the interesting thing is that these analyses can be used to put constraints on the fraction of dark matter with a certain total mass, and also on the merger rate versus redshift. And in the latter case, we can actually push a bit further away the estimate that we get from population studies, because with lensing, you can see also sources that you wouldn't normally see because of the magnification. We also have cosmological studies where we leverage the fact that the gravitational waves allow us to infer the luminosity distance, but then we have a problem in general because we don't know the redshift. We measure redshift masses and not source frame masses. So then where do we get the redshift from? Well, if it's a bright siren, then we can get it from the electromagnetic counterpart. If not, there are some other methods. For instance, if we knew the source frame mass model, then we could break the degeneracy because we will have both detector and source frame masses. Or we can also try to infer statistical the redshift of the candidate from the fact that we know the redshift of the galaxies that reside in the volume that we get from the observations. And there are other methods that I won't mention here because I don't have time, but essentially these are the constraints on H0 that we are getting with two of these methods with the latest catalog of events. And you can see here that for now we are not really able to solve the tension, but hopefully with more sources and better knowledge of our population and better localization, we will be able to reduce the posterior distributions on H0. Then, as I said, we perform also population studies. We have observed all types of binaries that we were hoping to observe. And we start seeing some interesting things that could be useful for constraining physical formation channels. For instance, some peaks in the differential rate as a function of primary mass, or some hints of correlation between effective spin and mass ratio, then again could be useful for population synthesis models. Then we also, as I mentioned at the beginning, we also look for continuous waves. These are long duration, nearly monochromatic signals. As I said, we have the main source that we expect to detect are fast spinning galactic neutron stars with non-axis symmetric deformations. This would come from a variety of phenomena, accretion, crust deformations, and so on. But recently, we also performed some searches from the emission from scalar boson clouds that condensate around black holes, spinning black holes, because essentially here you're using the super radiance to extract energy from the black holes, and you form this condensate around the black hole, and then the condensate annihilates, well, the bosons annihilates into gravitons and emit this quasi-monochromatic signal that happens to look quite similar to what people have been looking for in terms of neutron stars. And you can see here on the top right table that the characteristic amplitude strain that we expect for long-lived signals from rotating neutron stars is actually very, very small, much smaller than the one that we expect from compact binary coalescences. But this shouldn't actually deter people from looking for these signals, because the advantage that these searches have is that they can integrate the signals that they detect over a long time. And so essentially, because the sensitivity of the search goes like the inverse square root of the observing time, that means they can really dig into the noise floor to find these very, very faint signals. And here I will just mention one of the many searches that the collaboration performs. These are the targeted searches. Again, this is a synergy between electromagnetic and gravitational wave observations, because here the frequency and spin down rate are taken from EM observations. And there are several searches probing also different emission mechanisms that could be due, for instance, to the existence of a pin superfluid component in the interior of the neutron star. I will quickly mention all the other searches because I'm running out of time. We are also looking for stochastic gravitational waves, transient gravitational wave bursts. But again, all of the searches, they didn't produce detections, just upper bounds. And finally, I just want to quickly mention two things. There are some searches that could give us some hint regarding the presence of dark matter via direct interaction with gravitational wave detectors, but also by searches of subsolar mass objects, continuous wave searches, as I mentioned, but also from lensing. And I just want to conclude with this slide that is giving you a prospect of what is going to happen in the next years. So after 04, that is going to end next year in June, we will have another observing run, 05. And somewhere in between 04 and 05, there will be significant upgrades again to the detectors, resulting in A+ sensitivity. And then again, post 05, there is this plan of having a new, even more sensitive instrument, A#. And you can see here the sensitivity curves of all of these planned instruments. And we could have potentially an order of magnitude increase in detections after each upgrade. So thank you very much.
Thank you, Marta. Time for one question. The usual. Go. Yeah.
Thank you very much for the nice talk. You have, given us such a fantastic source, GW17817, that spoiled us in our expectations. And you haven't seen anything yet, although you've been looking at it.
Yes.
At what point do you start worrying?
So the current estimate for O4b to observe another binary neutron stars, the probability, I think, is around 80%.
One more.
One.
Okay.
Then there are estimates even for more, but obviously the probability decays.
And if you don't see that one?
We're optimistic. And there is O5 then, so.
No, finito. No.
There's also usual confusion that we make, but okay, thank you again, Marta.
Yes. we have to be optimistic in a certain sense, because I just received from Wang Yu a very nice number of citation of our meeting. And we have passed 100 million listeners in China, which have followed. And in addition of that, we are really continue to have the pleasure to see this fantastic work and share with all of you. Thanks.
Okay, Fulvio. Now, welcome to Fulvio Ricci. You will talk about the future and the Einstein telescope. 20 minuti, poi 5 e poi no, ti do 5 minuti, perché poi 5 minuti per le domande.
What happened yesterday? It's okay? Oh. Okay. Now, let me first thank Remo and the organizer of the conference to invite me to speak about the future. Future means the third generation of gravitational wave detectors. Just to give you the scenario in which we are moving for the gravitational wave observation. We are in practice at the level of the time in which we were observing with the electromagnetic radiation the universe with the rudimental telescopes. And to do better, we need a new instrument. And this idea to do new instrument is something that is always what is pushing for having the progress in physics and in astrophysics. This is the present situation that you have seen from the Marta talk, that mainly is focused on the detection of black holes and coalescent binary systems. Then we are setting with our advanced detectors several upper limits, which are extremely interesting. But then we need signals. We need signals not just for progressing to understand the physics of the black hole, but even to understand other kind of events like supernova events, the equation of states of the neutron stars, and the stochastic black holes. We will progress in the sensitivity with the advanced detector. This is the example of Virgo. This is the experimental, this is the experimental sensitivity of Virgo. And we see that we have a lot of margin in the joining the final configuration that is depicted in violet on this plot. But then we want to do better than that, because this violet curve in practice is limited by the nature of the infrastructure that we have built. We cannot increase, for example, the length of the arms of the interferometer. And to do better, I have done a mistake. To do better for us means to go from the optimum frequency, the maximum sensitivity curve that we can achieve with an advanced detector of second generation, to go down to at least a factor 10 in all the frequency range. This is our target. And this, the idea to do in the direction to develop at least the conceptual design for having a new instrument is something that is born well before 2015. You see, these are the progress in the advancement of the conceptual design of ET. We started thanks to the European support that pushed for having a better networking activity among the European community of gravitational waves, but then extended to our American colleagues and extended to to the Japanese colleague. Europe supported even the ELITE project not far from the epoch of the first detection. Now, the situation is that we have a conceptual design which is dated in 2011 and reviewed in 2020. And we are at the level of having a formal ET collaboration which is formed. ET means a new infrastructure. The slogan is the following: it's a new infrastructure which is capable to host future upgrades for decades without limiting the observation capability. So we have to think this as a system that will evolve in time in terms of sensitivity, with a time life for this infrastructure that should be of the order of, as minimum, of the order of the 50 years. And the idea behind the Einstein telescope is to have several detectors, but when we are speaking about detector, we are speaking about a system of two interferometers. Two interferometers form one detector. Why this? The idea is to have to split the problem to improve the sensitivity in the low frequency zone, in the low frequency bandwidth of the with a cold interferometer, and to improve the sensitivity in the high frequency with a warm interferometer. What does it mean cold and what does it mean warm? In practice, in the this detector, the ETHF, we will store megawatts of power, light power, circulating into the detector. I am not able to find the laser here. Should be this one. I don't see it. 3 megawatts of power. In this case, the power is much lower. We are at a level of a few kilowatts, but the mirrors are cooled at cryogenic temperature. This implies to develop new technologies for having this concept that should become a reality. That is the best solution, technical solution. Okay, and you see the effect of this choice to have two interferometers in one detector. In practice, the cold one is improving the sensitivity in the low frequency zone, while the warm one is playing a role, a crucial role in improving the high sensitivity. And the combination of the two detectors, the two sensitivities, the effect of the two detectors will permit us to increase, to achieve the target to have a factor 10 better sensitivity to the respect of the second generation of detectors. The fact that in Europe we were pushing for the study of a third generation detector induced even a similar study to be carried on in the United States. And we have in the United States another concept of third generation detector, the US approach. In this case, we have the idea is to have, even in this case, two interferometers, one of different lengths. Different lengths because having different lengths, you see that again, with the 40 kilometers broadband, you have a better sensitivity in the low frequency zone. And with the 20 kilometers, you are recovering the loss on sensitivity of the 40 kilometers in the high frequency zone. But this is the concept that is under study in United States. but it's obvious that the two communities, the US community and the European community, have a lot of exchange, even from the point of view of developing the technology. The idea and the target is to have the possibility to look far at the level for the black hole physics, at the level of exploring what is going on in the dark age, when in the zone where the astronomical objects are formed, while at present we are exploring in practice this zone of the universe has Z equal 1, and probably when we are pushing the sensitivity of the advanced detector, we can arrive at zeta 2. So the jump is extremely ambitious for the third gravitational detectors, but I think that is what that must be done. This is a plot that you have seen several times during this conference. Was commented already by Lorenzo Amati yesterday. Then you have seen the plot presented by Marta that gives you the idea of the horizon distance for the neutron star coalescent, and black holes. And it is interesting to notice on this plot that is adding an extra information on the effect of the two different sensitivity curves for the Einstein telescope and for the Cosmic Explorer. You see that apparently in the low mass range, the Cosmic Explorer should perform a bit better to the respect of the Einstein telescope, while Einstein telescope is performing much better for which concerns the higher masses. That is because the Einstein telescope is pay a lot of attention on trying to develop an instrument which is much more sensitive in the frequency band between 2 and 10 Hertz. We are speaking always about black hole physics, but there are several other scientific targets and several contribution in the domain of fundamental physics and cosmology and in astrophysics. I don't want to read the long list that, by the way, is even incomplete on what can be done beyond the black hole physics for with instruments like a Cosmic Explorer and Einstein telescope. But this has been each of these topics has been a object of specific studies and simulations to guarantee the possibility that achieving this sensitivity, the goal is a goal realistic. As I said, new instrument means new experimental challenges. And the new experimental challenges, let me go a bit dividing the problem for the high frequency and the low frequency part. High frequency means having as scientific targets the search for primordial black hole, the dark matter candidates, and challenging the string theory. And in particular, I think I like a lot to stress the possibility to study much better in much more details the problem of disentangling the black hole quasi-normal modes, taking advantage of what Luciano discussed yesterday, not just for the black hole, but even for the neutron star, in particular to probe even this second point, to probe the equation of state of the neutron star, looking at the ring town part of the waveform in the case of the coalescence. This is the plot that gives you the meter, the feeling of the contribution that you can have if you are increasing significantly the neutron star. What is the experimental challenge? One of the main experimental challenges that we are in front. For the hot interferometer, we need a optics which is much better than the present one, that will be much better than the present one. In practice, we are speaking about an optical system that must be perfect with 3 megawatts of light impinging on the mirrors. And this means that we should be able to compensate sub-nanometer surface figure for the distortion due to the temperature. And this is a technological challenge which is extreme. It's not easy to be achieved. For the low frequency part, there are several aspects. One important aspect is the fact that if we are looking and we have higher sensitivity in the low frequency part, we have a signal with longer duration in the phase of the coalescence. So we are increasing a lot the signal to noise ratio, and we are playing a better role in the giving a warning, a trigger well before the merger, the time of the merger, and this will improve a lot. This is the impression that we will improve a lot the electromagnetic follow-up. Low frequency means low temperature. Why low frequency implies low temperature? This is the comparison of the sensitivity curve in the case of the ATLF interferometer at room temperature and the ETLF interferometer at cryogenic temperatures. And you see that the sensitivity curve is improved of at least 1 order of magnitude. This is an old lesson that we have. If you are carrying on the experimental low frequency, we can take advantages, for example, on the fact, not just on the fact that the thermal noise is reduced. Here in this zone, we are dominated by the thermal noise of the suspension, but we can take advantage also from the fact that we can use superconducting electronics, and superconducting electronics is a great advantage for this low noise experiment. This the old lecture which is coming from William Fairbank. The use of cryogenics in the interferometer, in a gravitational wave interferometer, is something that is going on in CAGRA. So we are learning a lot from the CAGRA experience. The experiment, Fairbank was saying, at low temperature, the experiment is the best, but I have to say that Bill Hamilton, a former student of William Fairbank, was adding, which is much more complex. So we have to cool down the mirror without touching it. The things are not easy. And but low frequency is important. We cool down the mirror, but even there are other problems which are connected with the noise at low frequency. It's a challenge to reduce significantly the noise which is associated to the control of the mirrors, and to reduce the noise of the stray light. And this imposes a review of even of the control strategy, and probably to review and to change all the system, electronic system that we are using for controlling the complex suspension system. In practice, what we have to do is not just to improve the sensitivity in this zone, but we have to improve even the sensitivity below 1 Hertz, because the RMS, the integral of the noise in the frequencies below 1 Hertz, play a role in reducing the dynamics of the control of the interferometer. Then, last but not least, the other challenge is to reduce another effect, which is playing a crucial role even for the low frequency, is the Newtonian noise. Newtonian noise is associated to the fluctuation of the gradient. So the microseismicity is moving the surface, and this effect is gravitationally coupled to the mirror, and this determines a noise effect that in principle cannot be screened. So how to solve this problem? The problem is solved in two ways. One solution is to install the system in a quiet environment, quieter from the point of view of the microseismicity. For example, this is the comparison of the microseismicity in Sardinia and the comparison of the microseismicity in the location of Virgo. And the second game that we can play is to try to implement a feedback, a software cancellation based on the measurements of the microseismicity of the ground, which is not easy at all. Then let me tell you about the status of this project. ET has been reviewed in the context of the Forum of European Strategy for the Research Infrastructure in 2022. And the review was a success. So we are in the list of the future research infrastructure for Europe. But the challenge, the review of the experimental configuration continue, mainly pushed by the European research agencies that will be the main actor to finance the system. So there are several studies that are challenging the choice, the main choice that we have done. The main choice essentially is to have, for example, one triangular detector in one site. This is one analysis of the scientific perspective under possible variation of the detector design. Instead to have a triangle in one side, to have a 2L far one to the other and see what is the cost, the analysis of cost benefit of the two solutions. And the other problem that we have to analyze and challenge is the choice to have two interferometers for each detector. In the case of the triangle, you see in practice what we have is to have in the same location three different detectors. That means six interferometers. While in the case of the 2L, we have in practice 4 interferometers, 2 detectors, which means 4 interferometers. This analysis has been carried on, is the results of the scientific impact of this analysis is the results of a group of people of the collaboration that published these results in Journal of Cosmology and Astrophysical Physics. A very interesting analysis. I tell you essentially that the fact that apparently there is all the configuration that has been analyzed give you as a result the fact that we have a significant improvement with respect of the advanced detector. But apparently something goes in the direction to tell us that 2L of 15 kilometers seems to give us a gain for the detection of several signals, so a factor 2, a factor 3, an improvement of a factor 2, a factor 3. Then there is the problem of the cost, which is must be analyzed. Even the T collaboration, as I said, is formed. We have the organization is based on research units. There are 90 research units, 1,684 members, the total of 243 institutions which are distributed in 29 countries. The majority are in Europe, but there are now contribution coming from also from the other continents. There is a strong facility, a strong development of facilities to test the cryogenics. This is just a picture that show you a few of them. The sites that has been proposed to locate the detector formally are two, one in Sardinia, the other in the region at the border between Holland, Germany, and Belgium. There are studies even for other two sites. One which is rather advanced is in Germany, near the border between Poland and Germany. And now, more recently, it popped out also the possibility to look at the site in Spain. Formally, the two strong and well-studied sites are these two. I mean, the Terziet site in Netherlands, and this is in Sardinia. And these are the studies that has been carried on from the point of view of the qualification of the microseismicity of the two different locations. I go to the conclusion of telling you that give you some information concerning the financial support that we got up to now. The investment for the R&D to carry on to complete the conceptual design study is significant. In Holland, there was a strong financial support of the order of 42 million euros for the organization of the R&D to set up the so-called laboratory of a key pathfinder. In Italy, we had 50 million that comes from the Italian Minister of Research and University to realize a feasibility study for installing a T in Sardinia and to study the new technology to be implemented in ET. And we got even the promise that if we are able to have ET installed in Italy, the Italian government promised us to invest almost 1 billion to have this infrastructure installed there. Finally, timeline. The ET science case is based on a so-called blue book that we have to update in 2024 and 2025. We should freeze finally the geometry and choose the site probably within 2026. And in the same time, what we need to be done is to have a legal entity that in any case can manage this huge infrastructure that will be born in Italy. And this is the case both if we will move toward the direction to have two detectors not co-located or just one detector. In any case, we need an European, an international legal entity that will manage this structure. That's all. In practice, as I said at the beginning, we opened the observation of the universe with gravitational waves with the second generation of interferometers. Now, the goal is to go on, to go toward the construction of the third generation of detectors. And what is going now is that we are working hard toward making it a real observatory. That's all.
Okay. Thank you, Fulvio, for your brief glance to the future. A couple of questions, because we're running out of time. Let's see one there.
Thanks for your nice talk. Because of the increase of the sensitivity for ET, will there be a problem for the signal confusion in the data analysis? The signal confusion for there will be the overlap of the signals from the binary black hole mergers.
The main problem of ET from the point of view of data analysis, there is a group of people which are studying deeply in this matter because we have a real problem of overlap of signals. And we need to understand how to manage this huge overlap of signals. And we need to define a strategy. We need to define a methodology how to analyze the data. We need to define even the infrastructure that we need to carry on to solve the problem. So is something that is on the way. How to deal with such a kind of problem, and the gain in terms of information that we can extract with this plethora of signals will be enormous. From even because if we cut the signal in function of the signal to noise ratio, we will have in any case, compared with the advanced detector, many candidates on which we can perform, for example, test of GR with a huge improvement in the accuracy.
I couldn't miss this.
Yeah, thank you. A very short comment. I think it's important to stress the synergy between ET and other Italian-led efforts like Teseus, which will really be a fantastic complement in the electromagnetic detection of gravitation, not of gravitation or gamma ray burst. I think the two can really make Europe the center of all of this physics.
I have to admit that I haven't stressed the aspect of the multi-messenger astronomy, the role of ET in boosting the multi-messenger astronomy. I haven't stressed it even because yesterday Lorenzo Amati has already given the flower of that. It was a wonderful talk of Lorenzo, and probably I thought that this was enough. Okay, I agree with you.
No, just we had a very long week and lots of results in the week. Somebody arrived here at the end, but there is one topic which you should be aware, which happened on Monday. Namely, we think there is a problem with the analysis of black hole, which was adopted for making the prediction and the observation. In the black hole formula, there was one term which has been neglected, the irreducible mass. And this has some fierce consequence on this topic. For everybody else participate, we have a lot of material coming up, but I just want to make you aware that there is this black hole is not only formed by mass, charge, and angular momentum, but is also present in the irreducible mass. And therefore, during the signal, the surface area of the black hole cannot be constant. I don't know, well, but it must increase. and therefore that create a problem. Not a problem, create a solution to many problems.
Okay. Thank you, Remo, for your last remark. And thank you again, Fulvio, for your talk. And now we are pleased to welcome Roberto Ragazzoni, the newly appointed president of National Institute for Astrophysics, INAF. So he's the most suited person to talk about the future facility of INAF. Thank you.
Okay, so thanks to everyone. Thanks to Remo Ruffini for this invitation and to Massimo Della Valle to have raised it out of the noise of the Avogadro number of mails. And I was asked to speak about an overview INAF's involvement in observational facility. Of course, depending upon the degree of involvement and what is exactly an observational facility, you can place a lot of things of a very few selected things. So first of all, I want to make a disclaimer that I am going to show you a biased view of what is actually the INAF involvement in observational facility, biased because of my previous involvement. I build instrumentation mostly in optics, both from ground and from space. So clearly there is a bias in this sense. Also, I try to be as wide as possible. And because I had to pick up some choice, I will try to understand in a minute. So sorry at the beginning for these things. So there is also a second issue that is how to organize this in order to make an overview. You can make a very classical, this kind of things of classical upon the wavelength, of course, with the entrance of gravitational wave and neutrinos astronomy changed our view. Is not just one parameter, the frequency or the wavelength, depending which part of the right or left side of this table does change, or to science. I mean, okay, so we, for example, I did not made any example of observations of our solar system. There are projects for observatory to observe the sun, for example, or to go to the planets in the solar system. I didn't classify this as observing facility, but of course there is a lot of involvement in INAF in this kind of observation. So sorry for anyone that are not, mentioned in these things. While exoplanets is maybe a bit different. There are a lot of observatories carried out for looking exoplanets in our neighborhood. There is observational facility to look at stars and observational facility that goes a much larger distance that they overlap with the cosmology. I also remind that I understand that probably most of you are theoreticians, so maybe I am in the den of lion from this point of view, because I am one of the persons that usually build instruments. So there is another very, very strong division of observing facilities, that is what is on the space and what is on the ground, not only because for several reasons. INAF is clearly involved in all the space stuff, but of course this has a strong implication and relationship with the Italian Space Agency or other space agencies, if there are bilateral, and the European Space Agency or with other space agency, while on the ground, this also involves organizations, and usually today, most of the larger facilities are not placed on the Italian territory, with a few exceptions. So, first of all, the first obvious thing is that we want to go to larger telescopes. Making a larger telescope is a mantra, because of course you collect more light, just like having a big funnel, and because you have a better spatial resolution, because our usually, most of the observation are background limited. This means also deeper, better, deeper limited magnitude reached by this kind of observatory. So this is a classical example of the difference between the Hubble and James Webb. I will say that there is enough involvement in both, of course, for several reasons. In the JWST, mainly because, and substantially only because of the involvement in observing data, and but there is, of course, an industrial participation. We were with a little participation in MIRI, one of the instruments, but this is not anymore, while we had the participation on the other HST, and we are trying not to make the same, I believe, mistake for the Habitable World Observatory. That is basically the next space telescope, but this is a very long site. I'm not including here any discussion on this, but I just was willing to mention. So I try to make a very non-exhaustive list, the ground-based observatory. Of some of this I will not speak later, but I want to say a few words. We have a little but significant participation, especially because on our technology from the Institute of Radio Astronomy of INAF for LOFAR, very low frequency. This is a telescope that is they like to say the less apparent telescope in the world, because it is just some boxes in the field, and this covers a large area. The frequency is very very low. The wavelength is very long, so they need large distances. But now everything is digital. This is LOFAR. SKA is a great idea, the square kilometer array. This is an idea that dates back to the turn of the century. Basically, is now becoming a reality. I will maybe speak slightly about that, but it is just maybe you also remember that there has been a situation which it could be that the headquarter was in Italy, actually in Padua, but it's now in Jodrell Bank, and the two observing sites are from South Africa and South America, and I'm very happy that also in the last council of a few days ago, I mean, there's been an agreement, for example, with Starlink to avoid that they beam their emission for communication on the two sides. So this is a good thing to preserve from the radio viewpoint. ALMA produced a lot of great things, especially on dust. We have the Sardinia Radio Telescope, and of course there is also the Italian VLBI. Then we have a strong participation in the VLT of ISO, the 4.8 meter class telescope. In LBT, we still, of course, have the TNG in Canary, the 3.1 meter telescope. And CTO and Astria, I would say this is, for example, the area where we invested till now in the last years as the largest amount of money, basically. I mean, it's a Cherenkov telescope. We'll briefly speak later. On space, we are on HST and GWST. We have a strong involvement in Gaia. We made also several hardware, and we are great involvement in Euclid. We are all in the observatories for exoplanet, Cheops, Plato, Ariel. The X-ray community is a large X-ray community. I just placed XP here. I didn't mention Theseus because it's not yet approved, but if I start to make all that, in principle, one should also write Athena. There is also the spreading with the Chinese for the X-ray telescope and so on. I could not cite, of course, Multimessanger. I will speak briefly of this in a few minutes. So I am pretty sure I'm forgetting something. Sorry about this, but was just a first lead. It's such a situation in which we are not even able to say today which is the largest optical near-infrared telescope, where at least, I mean, we can have in principle, it is easier than a radio telescope or X-ray telescope, where the collecting area is significantly different from the size, while here the obstruction is always a few percent of the light. Even in this case, it's not clear which of these three telescopes is the largest in the world. We, however, as INAF, have a deep involvement in two of them in the LBT, in the VLT. So 2 out of 3 of the largest telescope today in the world in the optical near, we are deeply involved. And of course, we are heavily involved in the extremely large telescopes. This is a 39-meter segmented telescope that is under construction with a lot of Italian, both industry and scientific community involved in the realization of the instruments. I will come in a minute in this. But let me speak slowly about, briefly, sorry, about SKO. I mean, this is, for example, antennas, arrays of antenna deployed in in South Africa, to give you an idea. So the idea is to have the equivalent of a square kilometer, but scattered on an areas that is order of 100 kilometers to produce interferometers. They are almost arranged like a spiral, not a perfect spiral for practical reason, because in some places it is not possible. So there is a discussion, the optimization of the exact location, in which we are, I would say, one of the after the, let's say, UK, South Africa, and Australia, that are one of the main, and China, one of the main partner. We are one of the largest partner after this, where the telescope is already physically located. MERCAT and SKO also include lower frequency antennas that has been developed in partially also by us, and so this is an idea of what will be this array of telescope. Let's switch from radio to optical visible. This is a night picture taken at one of the VLT telescopes, the UT4, that is equipped with 4 lasers to form artificial laser guide star. Let me remind that we in Italy, let's say, I would say, enough master, I mean, the technology of adaptive optics, of controlling the wavefront of the light to get a better resolution, both in terms of wavefront sensing and deformable adaptive mirrors that are today basically upgraded to every telescope in the world. And there are a lot of discussion about going to bluer wavelength. Usually this was confined to the near infrared. Now we are moving to the visible, at least to the reddest part of the visible, but the idea is to push the technology to go to bluer, to have a higher stress ratio, higher contrast, and to have larger field of view also for thin spectrum. I will briefly speak in a second. So let me give some example of things in which we are heavily involved. This is, so it's not only on the large telescope, but also instrumentation. This is ERIS on the focus UT4. In fact, I mean, the drawing then become reality in the right side, and you can get an idea of the resolution. This was now the adaptive optical VISO, the classical one, let's say in this way, and this is the AO that we are able to obtain. You can see the difference in resolution and in depth, as I mentioned before. On the LBT, we have a bit more, I'd say, challenging instrumentation. I mean, so we accept to have a little more risk. So we have this an instrument that have a relatively a bit of larger risk with a chronograph with a higher order and a way to make compensation inside the telescope. Then, as adaptive optics is not only confined to looking for planets or for disks, but we want to push for having an extragalactic thing. We are heavily into MAVIS. MAVIS is a sort of precursor, one of the VLT, to make wide field adaptive optics, so having diffraction limited from the ground on larger field of view that today is only achievable through space telescope. And the goal of this instrument is to make it normal to have wide field diffraction limited imaging on the ground. In fact, the very big instrument on this field is Morpheo, was namely called Maori before, I suppose, to feed Mikado in order to have imaging on the extremely large telescope. Then we are very heavily also in the spectrographic part, so to use adaptive optics in order to improve the capability of the high resolution spectroscopy. This is a locator that is to be mounted on large binocular tapers. And on the right side, Alessandro Marconi, we signed recently the agreement with ISO to pursue this development of this spectrograph that will be adaptive optic assisted on the ELT, on the 40-meter class telescope. So the exoplanets get a larger and larger, portion of community involved. So I just show you what, accordingly to ESA, is the plethora of the armada of instrumentation in space for the purpose. You see Kepler and TESS from NASA, and of course James Webb, that is a joint things, without forgetting Gaia, that with this very precise astrometry is making a lot of contribution. But you see there are Cheops, Plato, and Ariel, three instruments, one out of the other, in which INEF is heavily involved on this. They basically change the paradigm. Kepler looking for a large number of stars for looking for transit. So in this cartoon, I made like 1,000 stars. Kepler is looking going deep, and so this mix, and most of the exoplanets are found around a faint, faraway star, while Plato, that is in advanced phase of construction, and will be launched with Ariane 6, that has been finally, checked less than a week ago from French Guiana, making this on a wider field, so observing basically exoplanets around the bright stars. So I will skip this. I don't want to. So this is turning into reality, and I also like to remind that while we had a couple of, so each of the telescopes is named to some person, and further to two historical figures like Giordano Bruno and Cristina Roccati. We also named the one to Angioletta Corradini, was a spectrograph, is visited from Venus to Mars to Jupiter to Saturn, a lot of places in the solar system. So these are the final test of Cheops, another telescope built in this situation. Okay, I will skip, and there was a movie, but it doesn't matter. So there is other telescopes that are producing a lot. So there is a lot of interest in the community about this, and the Italian involvement is very large. So now let's speak about more closer, thanks to my previous speaker, so I will not have to describe in detail. Of course, the Einstein telescope is led by INFN, so we are, of course, partner in this, and for example, the technology of the adaptive optics, there is a branch of the study to see how it could be adapted to actively control the shape of the mirrors of the interferometer in the tunnel that was mentioned just before, as we have a large experience on this, of course, in a completely different environment and on different complete figures. So it's unclear in this moment how will be the outcome of this, but surely, this will, on the multi-messenger side, there is a connection with how much will be possible to detect simultaneously. That's my view. Or, as soon as you have a trigger from the observation in the visible or in the gamma, this is on the X-ray, this has been already mentioned. I am not mentioning here Hermes, and one possibility to have a larger version of Hermes, to have a constellation of satellites to have the X or gamma ray detection in real time. Theseus has been already mentioned, and of course, it's a mission in the hands of ESA in this moment, and of the Lorenzo Amati, of course. But what I want to stress here, I taken this from the same paper has been mentioned by before, that whatever is the configuration with 2L, with the triangle, 10 or 15 kilometer, 20 kilometer, the field of view, the error bar where you see, where you see the object is always of the order of a number like 40 or 100 square degrees. So it's not, and usually when you go to observe, you find a lot of transit there. So I think that large telescopes is not only having a largest aperture, you go for a 4 meter to an 8 meter, and you have 4 times the area. So of course, you look, deeper, but also, the field of view that you collect. So what does matter in this case of science is also the A times the aperture times the omega times the field of view. So if we speak of telescopes with larger A omega, there is I use it broadly the word involvement in this way. For LSST, for example, we are now from a couple of years partner with some our expertise on checking all the telescopes. Our people from MENA feeds at the sites where LSST is being erected to help to the construction of the telescope. It's a 6.4 meter with almost 10 square degrees. So there are numbers and they start to be relevant. We have been involved from several years in FlyEye. So we have this is mainly now used by the Italian Space Agency for debris, and we are looking so completely alternative ideas to have 1 meter class telescope looking simultaneous as the whole sky. So I believe is my last 2 slides or 3 slides. I mean, I mentioned the Cherenkov telescope. So this is, there are both CTAO and ASTRID that are both in Chile and in Canary, are telescopes that basically looks at the secondary effect of gamma rays. So the actual detector is the atmosphere, and you see a side effect of the gamma rays that enter the atmosphere. This is not new, I mean, but we are building several classes, small, medium, and large Cherenkov telescopes to cover all the possible energy, including beta electron volts, gamma rays. And the second one relate to just, I wanted, as I was asked, to speak of large facilities in which INAF is involved. I try to make a bit of jokes, trying to see which is the largest facility in which we are involved. And you know that this picture of the of deep field with JWST is actually made by a natural gravitational lens. And I played with the fact that we can claim that they are being involved in telescopes of the size of 10 to the 20 meters, just for fun. So that's the whole. And again, sorry, because I'm super sure that I missed some of the instrumentations that are still supporting. INAF is supporting a lot of a wide variety of instrumentation. Thank you.
Okay. Thank you, Roberto. There are some questions. I'll be able to take them. Well, I have a
understanding that he will be the first lecture which you don't get. You have to invent. Sorry, I'm kidding.
Do you have a question? Strange. That's very strange. This is surprising me. Well, maybe I just a short remark. You quoted a lot of facilities, multi-wavelength, gravitational waves, neutrinos is something that INAF should take care.
Yeah, you're right. I mentioned it as the multi-messenger, but we are not really involved. Or maybe we are, and I'm not aware of. It's not impossible.
No.
Thanks, Fabio.
Yes, Remo could refer to.
Well, just to thank for having honored us at the early stage of your presidency at INAF. And needless to say, we all look forward to a very strong collaboration with you. And I am very happy also that you came, because to our distinguished guest from a foreign country, like the head of some of the most important mission, the Einstein telescope, just flew in to to give the first data of the Einstein telescope in China, which was developed also with the participation of Italy. And we look forward to have a very intense relation with you. And we thank you also on the name of the Oterikranet member from Armenia, who is here. And come, Professor Sakian, who is the director of Ikranet Armenia. And all together, we are very, very grateful and planning to go further. Very impressive, this gravitational lens, possibly the largest ever seen yet. But we all appreciate that you make that choice. Thanks again for coming. Maybe I will introduce some of the distinguished professors. There are so many, but at least the one who came from farther away. Can you come? Yes. To introduce you. What about?
Can I have a microphone?
Yes.
Okay, before we finish the session, I'd just like to have a small possibility. Since we were going to still have afternoon sessions, but we have the final gathering of the meeting in the plenary session here today. So I'd like first of all to thank very much the municipality of Pescara, who actually gave us the place where we are located now. You see this beautiful image from above. We also are thankful to the University Chieti Pescara, D'Annunzio, which actually hosted us at the largest building they have in the campus. We are deeply grateful to all the chairperson whose multi-year effort and help actually give the possibility to run the meeting for successful editions for the 17th edition so far. But the real great deep help which was actually provided by the local organizers here in Pescara, Elisabetta, Monica, Cristina, Sabrina, Silvia, Cesare Corsetti, multi-year helper, and of course our genius, IT genius, Luciano. So we're really deeply helpful, grateful to their help. Thank you so much.
Yes, I think it's you really. I really like to thank you a lot because you did something exceptional, and thank also the University of D'Annunzio because the University of D'Annunzio is close by, has two campuses. We will not have the time, maybe a few minutes, but we are only 1 kilometer away. And there is another campus in Chieti, very, very big, which I hope you will visit. But the interesting thing from our point of view is the first time that relativistic astrophysics and physics and mathematics were introduced in this campus because it's a fantastic university with 25,000 students. We are close by and we are trying to insert them in ICRA and in ICRANET and open this beautiful campus to physics, astrophysics, and for mathematics and so forth. It's a great opportunity. But Pescara deserves this attention. See? Yes, yes, yes. The Einstein probe is the director. He just left the telescope to come here to give the lecture and bring us the first data. And no, Liang, come. And Liang is the head of the graduate school of the Chinese Academy of Science, which, as you know, is the largest, one of the largest institutions in the world. But he's also the head of a graduate school in Beijing, and is the head of one of the mission, the two mission
for Taiji program, yeah. For Taiji program is leading by the University of Chinese Academy of Science, which is the biggest university for graduate studies. We have now more than 60,000 graduate students. And is also supported by the Chinese Academy of Science for more than 100 institutes. And we also the Taiji mission, and we also have the International Center for Theoretical Physics, Asia Pacific, as a Category 2 center of UNESCO. So we hope to have the cooperations with e-Canada and also universities here and to develop our corporations. Thanks.
Yes, we have Yefei. Where are you? Yefei Yuan, you come in, come in, come in. When when the worst part is important, you know, this detail maybe they can be inspiring for you. When the worst part of the regime in Russia and the revolution of the student in 1968 paralyzed the university in Beijing, a professor, Yang Jiqi, which I have the picture, and I went with Amaldi to greet him, founded in the countryside, in the poorest region of China, a university to escape from the problem of Beijing. That small university, which I visited 40 years ago, is now the University of Science and Technology of China, and we have a joint degree with them. And with the University of USTC and Professor Yuan Yefei Wan is one of the head of our collaboration. And this is historical because from there, everything started to move. And then, of course, now the cast at the University of China went back to Beijing. But initially, it was in FA. And he's professor of this university and leading our collaboration agreement. Is that okay? Chi altri vuoi fare incontrare? And let's have a nice picture together.